শুনতে পাচ্ছি।
ঠিক আছে, স্যার শুনতে পাচ্ছেন তো?
হ্যাঁ, শুনতে পাচ্ছি।
ঠিক আছে অদিতি, এবার আমরা মনে হয় শুরু করতে পারি। স্টার্ট নাও।
একদম। ওকে, fine. Good afternoon and warm welcome to everyone. We are present here for the state level webinar entitled A Brief Survey on Selected Topics of Real Analysis and Geometry, organized by Department of Mathematics with IQAC Fakir College. Our Honorable Principal, Dr. Shoumen Chanda Sir, IQAC Coordinator, Dr. Proggamoy Pal, present all professors of our department and college and other college also. The resource persons, respected Professor Montu Shaha Sir and Professor Monjusha Mojumdar Madam. All the participants present here and Dr. Liton Balo, Assistant Professor of Electronics of our college. On behalf of our department and college, a deep, warm, heartful welcome to all. First, we are going to commence the state level webinar with inaugural session. I am inviting our Honorable Principal, Dr. Shoumen Chanda Sir, to deliver his inaugural speech. Please, sir.
Thank you, Aditi. Am I audible?
Yes, sir.
Thank you very much. I was tensed whether I will be able to join here or not because it has crossed 100. It's a good participation. A very good afternoon to the distinguished guests, speakers, dear colleagues, and students, and ladies and gentlemen. Today's webinar, titled A Brief Survey on Selected Topics on Real Analysis and Geometry, has been arranged by the Department of Mathematics in collaboration with the IQAC of our college. Thanks to the organizers, and I am very pleased to be present. As a student of physics, I used to feel an attraction towards mathematics to the studies of mathematical physics and its applications in almost all over the subject physics. It is said that mathematics is the language of physics, and I truly appreciate that. But then, it was not hardcore mathematics which I was attracted to. I got an inclination towards practice or practicality of the mathematical laws and formulations because my subject is more prone to explain the natural phenomena, experimental data, and thereby formulation of the underlying natural laws in the form of mathematical equations. But I feel that development of fundamental theory of nature has to have some good deal of mathematics, such as classical mechanics, quantum mechanics, general relativity, string theory, etc. In fact, Sir Isaac Newton was the first person who enunciated classical mechanics with his famous 3 laws, and in order to apply his laws to complicated system of particles or solids, he had to develop his own mathematical tools, which were either not known or not so well understood before him as far as solving a real-life problem was concerned. I would appreciate if any remarks in this talk is considered as of general nature. The abstractness of mathematics makes it pure because it has absolutely nothing to do with the existence of the nature or the universe. Its algorithms are all encompassing under certain mathematical conditions. Due to these characteristics of mathematics, it has become a separate branch of knowledge apart from the natural sciences. The first abstractness of it came to the human mind, I think. It is in the form of concept of numbers, without which it cannot start to speak at all. Geometry, and yet another branch of abstract knowledge, was a contemporary, although it is not clear exactly when mankind learned the techniques of counting or even became aware of the variations of the size of a gathering, while we find living species are still unaware even after so many million years of evolution. So, whenever in history the concept of numbers came to our mind, it came to solve a very, very real problem. That is, to calculate and compare the size of a gathering of animals, group of early humans, community size, etc. I think the power of comparing size of groups is inherent in human genome, so that mother could feel a loss of her offspring in those prehistoric days. But how? I do not know, and I do not know anyone who knows. So the technique of numbering developed to solve a real problem and gave the concept of real numbers. Well, at the same time, developed the idea of geometrical shapes also while solving the problem of marking territorial land. Some of the early people who were quite intelligent and prodigious later on put on a deep thought about the nature of the real numbers, their properties, etc., in order to satisfy their personal quest for advanced knowledge. In present-day mathematics, real analysis is the branch of mathematical analysis that studies the behavior of real numbers, sequences, and series of real numbers, and real functions. Some particular properties of real valued sequences and functions that real analysis studies include this convergence, limits, continuity, smoothness, differentiability, and integrability. Mathematically, any solution of an equation of the type x square minus a square equal to 0 is a real number. All these solutions form a set with respect to addition and multiplication operations and will be having the properties of commutativity, associativity, distributivity, while including null, unity, and inverse. Null or zero is the result of addition of a real number with its negative counterpart, and unity is the result of product of a real number with its inverse. So, inclusive of all these, the set of real numbers said to be closed or complete. But still there is a problem with an equation of the type x square plus a square equal to 0, where a belongs to the real set. This triggers the studies of complex analysis, which is another story. There can be 5 subsets of real numbers. Number 1, natural numbers, 1, 2, 3, etc. Number 2, whole numbers, 0, 1, 2, 3, etc. That is, which includes 0 with the natural numbers. Number 3, integers, 0 plus minus 1 plus minus 2 plus minus 3, etc. Number 4, rational numbers, which are expressible in the form of a ratio between two whole numbers, but with the restriction that there will be a finite number of digits after the decimal point when it represented as a decimal fraction. And number 5, irrational numbers, which are also expressible in the form of a ratio between two whole numbers, but having the restrictions opposite to the rational numbers. That is, there will be an infinite number of non-repeated digit sequence after the decimal point. It was long understood that geometry has got many things to do with measurement, and measurement needs real numbers to be expressed. More than 2000 years ago, a Greek mathematician from Alexandria named Euclid wrote a book titled The Element, in which he deduced many propositions or theorems regarding geometrical objects, assuming a small set of intuitively appealing axioms. Although many of his propositions had been stated by earlier mathematicians, but he was the first to show how these propositions could fit into a comprehensive, deductive, and logical system. The elements begins with plane geometry, still taught in secondary school or high school as the first axiomatic system and the first examples of mathematical proofs. It goes on to the solid geometry of 3 dimensions. Much of the elements states results of what are now called algebra and number theory, explained in geometrical language. Euclidean geometry is an example of synthetic geometry in that it proceeds logically from axioms describing basic properties of geometric objects such as points and lines to propositions about those objects, all without the use of coordinates to specify those objects. This is in contrast to analytic geometry, which uses coordinates to translate geometric propositions into algebraic formulas. For more than 2000 years, only the Euclidean geometry was known, and so there was no need to add the adjective Euclidean before the word geometry. Euclid's axioms seem so intuitively obvious that any theorem proved from them was deemed absolutely true. Today, however, many other self-consistent non-Euclidean geometries are known, the first ones having been discovered in the early 19th century. An implication of Albert Einstein's theory of general relativity is that physical space itself is not Euclidean. An Euclidean space is a good approximation for it only over short distances relative to the strength of the gravitational field. 3 famous types of geometry, type 1, type 2, and type 3, for zero, positive, and negative curvature of the space, respectively, have evolved since then. The fields of numbers and geometry are so profound that the stories cannot be spoken in one lecture or even in one day, maybe. So, let me stop here by thanking you for your patience. As we all are eagerly waiting for the speakers to speak, let me take this opportunity to announce the session open, and thank you.
Thank you very much to our one of the resource person and also the principal of our college, respected sir, for your exuberant speech. Your support and guidance always nourish us. Thank you very much. Now, I would like to invite the IQAC coordinator, Dr. Proggamoy Pal, sir, for your welcome address of today's webinar. Please, sir.
Am I audible?
Yes, yes.
Thank you, Aditi, and also my colleagues of the Department of Mathematics for inviting me to deliver the welcome address. At first, a very good afternoon to all the participants. I am much glad to welcome you to this webinar on my personal behalf and on behalf of our entire Fakir College family. As you all know, that today's webinar is organized by our Department of Mathematics in collaboration with the IQAC of the college. Today, our distinguished speakers are Professor Montu Saha and Professor Monjusha Majumdar. We are really glad and honored to cordially welcome both of you. Mathematics has no generally accepted definition. Aristotle defined mathematics as the science of quantity, and this definition prevailed until the 18th century. However, Aristotle also noted a focus on quantity alone may not distinguish mathematics from sciences like physics. In his view, abstraction and studying quantity as a property separable in thought from real instances set mathematics apart. In the 19th century, when the study of mathematics increased in rigor and began to address abstract topics such as group theory and projective geometry, which have no clear-cut relation to quantity and measurement, mathematicians and philosophers began to propose a variety of new definitions. Now come to the topic of today, a brief survey on selected topics on real analysis and geometry. In mathematics, a real number is a value of a continuous quantity that can represent a distance along a line or alternatively a quantity that can be represented as an infinite decimal expansion. The adjective real in this context was introduced in the 17th century by Descartes, who distinguished between real and imaginary roots of polynomials. The real numbers include all the rational numbers. The real numbers are often described as the complete ordered field. The real numbers are most often formalized using the Zermelo-Franklin axiomatization of set theory. But some mathematicians study the real numbers with other logical foundations of mathematics. In particular, the real numbers are also studied in reverse mathematics and in constructive mathematics. In the physical sciences, most physical constants, such as the universal gravitational constant, and physical variables such as position, mass, speed, and electrical charge, are modeled using real numbers. In fact, the fundamental physical theories such as classical mechanics, electromagnetism, quantum mechanics, general relativity, and the standard model are described using mathematical structures are based on the real numbers. With these few words, I am handing over the program to Aditi again, as I know that all of you are eagerly waiting to hear from our honored guests. Finally, once again, I am extending a very warm welcome to all of you in our present program. Thank you very much.
Thanks a lot to our respected IQAC coordinator, sir, for this affluent speech and support and guidance. The inaugural session is over, and we arrived in our next session, that is the technical session of the webinar. Our first speaker is respected Professor Montu Saha, sir. His topic is a study on representation theory of real numbers. Participants are requested to not to ask any question while the lecture is going on. Participants may text their doubts in chat box. After the completion of the lecture, we will discuss about your doubts thoroughly. All participants are requested to mute themselves during the lecture. Professor Montu Saha is an eminent professor of Department of Mathematics of the University of Bardhaman. He has numerous research papers in various reputed journals. Fixed point theory, topology, functional analysis, application of functional analysis are the fields flourished by his work. Now I cordially request Professor Montu Saha, sir, please cultivate our webinar with your valuable speech. Please, sir.
Am I audible?
Yes, sir.
Madam Ashish?
Yes.
Okay. So good afternoon, respected principal of this college, my dear learned friends, participants, and my dear students. First of all, I would like to convey my sincere thanks to the authority of Fakir College, Kolkata, and the organizing committee of this webinar program for inviting me to deliver a state-level webinar on a brief survey on selected topics on real analysis and geometry. Especially, I convey my heartfelt thanks to Dr. Shantanu Bhuiya, Professor of Mathematics of this college and coordinator of this webinar. So in recent times, that is, I mean to say in the pandemic period, due to COVID-19, for almost last 1.5 years, the college authority and the Department of Mathematics of this college have taken a right decision to organize such type of this program. Really, we the teachers are not getting in touch with the students to teach them physically, and we are not getting flavor using the chalk duster board method to teach students in physical mode. Students are also being deprived in learning mathematics from the teachers physically. They are losing their cherished mode in learning mathematics, what they would get physically. We really feel it. However, at present, we are doing work from home, that is in virtual mode, as for through online mode like Google Meet platform, WebEx and Zoom, and etc., etc. And we are accustomed with such type of technologies, and we are habituated now to learn mathematics, to teach mathematics, interactive with the research scholars. So we are now blessed due to the revolution of the technology. However, we shall have to go, in fact, we shall have to cope up with such type of the technologies whenever some types of crisis situations arises. Hopefully this phase will go down very shortly, and we will be returning back as usual, and we'll do everything as before we used to. Now I will not linger my talk. Already a few minutes have already been passed. Now we are going to discuss our main topic. I shall talk on a brief study on representation theory of real numbers. I will try to say in a very lucid manner and very selected topic, that is how the real numbers are generated, right? So I want to focus on such type of this topic. So am I audible?
Yes, sir, you are
Yes,
audible.
sir. Yes, sir.
So what is called real analysis? It is a development of the set of real numbers which is reached through a series of successive extensions and generalization starting from the set of natural numbers. As a matter of fact, starting from the set of natural numbers, and then we pass on successively to the set of integers, set of rational numbers, and the set of real numbers. Of course, from the set of the real numbers, we can also pass on to the set of complex numbers, which is beyond our scope in our discussion today. Is in our today's discussion. The study of elementary mathematical analysis that is basis of real numbers. We shall begin our development of real numbers with the set of natural numbers, and then we shall introduce a wider class, namely the set of rational numbers. So if the time permits, so we shall discuss on how the real numbers are generated by the Dedekind sections. Okay. So we shall divide my lecture in two halves, assuming the set of the objects called the real numbers, if they exist, and we shall view it as an ordered field having the least upper bound property. So Richard Dedekind's the span of life is 1831 to 1960 AD, make a different approach. He was a German mathematician. He looked the set of real numbers, a partition or cut of the rational numbers, which will generate either a real rational number or a real irrational number. So before going to start the representative theory of real numbers, we shall first start on the natural numbers. So first we shall start with the Peano's axioms. Peano is an Italian mathematician, and this axiom was discovered in 1889, and later it was named as Dedekind's Peano axioms. So what are the axioms? So if n be the set of natural numbers, if my board is visible,
Yes, sir.
Yes. So if n is the set of the natural numbers, and axiom 1 is 1 belongs to n, right? Axiom 2, for each n belonging to natural numbers, then there exists a number n dashed, which is called the successor of n. It is called the successor of n, right? And this successor is unique. Axiom number A3, the element 1 is not the successor of any element. That means n dash means successor means if n is a given, so n plus 1 equal to n dash. This next successive term is n plus 1. N plus 1 is the successor of n. But 1 is not the successor of any natural number. That means n dash is not equal to 1. Right? Now, axiom 4. If n not is equal to n for any two different elements, natural numbers n and m, their successors are also different. That is, n dash not equal to n dash. And if the converse part is also true. If the two successors are different, then the corresponding natural numbers are also different. A5. 5 axioms called the Peano's axioms. And suppose m is a subset of n, and if 1 belongs to m and m belongs to m, for which m plus 1 belongs to m. M is a subset of n. If 1, let us assume that 1 belongs to m and m belongs to m is obviously natural number, implies m plus 1 belongs to m, then m equal to full natural numbers. Then m equal to full set. Right? So axiom A5 is called the principle of induction, principle of mathematical induction. Later we shall see the time permits. So there is an equivalence regarding A5 axioms and another axioms. The time permits. Right. So you see how the natural numbers are generated. So this plays into the mind of Peano's. Right. So 1 belongs to axiom, first axiom, 1 belongs to n. Right. So by the second axiom, the successor means there is 1 dash for each element n, there is a successor. So there is 1 dash equal to 1 plus 1 equal to 2. That is for each n, there is a successor, that is n dash, which is equal to n plus 1. 1 plus 1 equal to 2. So by axiom A3, 1 is not the successor, 1 is not the successor of any n. So therefore we can say that is 1 dash not equal to 1. So 1 is the first element, 1 dash is the successor element, so therefore 1 dash not equal to 1. So therefore 1 and 2 are the two distinct elements, first two distinct elements. Now you go for the third element, how the generated. So for each n, there is a successor. So if 2 belongs to n, then 2 dash also belongs to n. That means 2 dash means equal to 2 plus 1, 3. 3 belongs to this. Now you see, it is 2 dash not equal to 1. 2 dash not equal to 1 by axiom A3, because 1 is not the successor of any natural number, right? So 2 dash not equal to 1, right? And also 2 dash not equal to 2. 2 dash not equal to 2 by axiom A4. What is the axiom A4? For two distinct natural numbers n and m, n dash not equal to m dash. So you see 1 not equal to 2. You see 1 not equal to 2. Therefore, by axiom A4, 1 dash not equal to 2 dash. That means 2, 1 dash means 2. 2 not equal to 2 dash is equal to 3. So therefore, 3 not equal to 2. So similarly, 3 not equal to 1. That is 2 dash equal to 3. 3 not equal to 1. 3 not equal to 2. So therefore, 1, 2, 3 are three distinct elements. Right? Now, if we continue this process, then we shall get, that is 1, 2, 3, 4, 5 and so on. Right? So you see how it comes. Now suppose n is a set. Suppose n contains 1, m is a set, 1 belongs to m, right? And n belongs to m. So by axiom A5, what we say, that is n dash is equal to n plus 1 belongs to m, right? So that means, so this, you see that this comes, as this follows as a principle of mathematical induction. So 1 belongs to m, n belongs to m, then n dash equal to n plus 1 belongs to m. So therefore we get the set of natural number 1, 2, 3, 4, 5 and so on. So that's why the natural numbers are generated in this way. Now algebraic operation. How do we define the addition and multiplication of the on the natural numbers? So definition of addition. So we have seen that for each natural number n belongs to n, already that is seen, that is n dash equal to n plus 1 belongs to n, right? So that means n dash equal to n plus 1. So how shall we define? So n plus p dash, what does it mean? N plus p dash equal to n plus p plus 1. So what it means? So n plus p plus 1. So this means n plus p dash. So n plus p dash equal to n plus p whole dash. So this is the rule of the definition on the set of the natural numbers. Say n plus p dash equal to n plus p dash. So it is a connection between the successor of an element and the original natural number, right? Similarly, this is the case for the addition. Similarly, how the case comes for the multiplication. So suppose we get n into 1 equal to n, right? In a natural number. So this belongs to n. Now n into p dash, what happens? N into p dash is equal to n into p plus 1. That means np plus 1. That is equal to np dash. So this is the rule of the product. That is np dash equal to np whole dash. So all the properties, that is associative properties, associativity property, distributive properties, and cancellation properties, and also the commutative property holds for the set of the natural numbers. I am not going in details. So associative property is n plus m plus n equal to n plus m plus n in case of the addition, right? In case of the multiplication, that is n into n into n. N into m into p equal to n into this. N plus m plus p equal to n plus p. Okay. So associative property, distributive properties, cancellation law. That means if n plus p is equal to n plus q, then this implies p equal to q. So similarly, n into p is equal to n into q by cancellation by law, we get p equal to q. So this type of the properties also hold in case of the natural numbers. Now, how do we define the order relation? How do we define the the order relation. Right? So suppose we are in the platform of set of natural numbers. So we are taking the two natural numbers, that is m and n, and this, and we define a relation, this m is less than n. So call it m is less than n. So that means, what does it mean? So there exists what does it mean? M less than n means there exists a natural number p belongs to n such that m plus p equal to n. M plus p equal to n. So m or n, two are distinct elements, so that m is less than n. So naturally we can find a natural number p belonging to natural number, set of natural number such that m plus p equal to n. Right? So already we have seen the corresponding to natural number n belongs to this, and we have achieved, we have got, that is n dash is equal to n plus 1 belongs to n. Right? So suppose 1 belongs to n, naturally 1 dash equal to 2. 1 dash equal to 2. So here that means if we relate the relations, that is n is less than n, that means 1 less than 2. Similarly, if we take 2, then 2 dash equal 2 plus 3 equal to 3. So natural numbers are related in this way. Okay? So
স্যার বোর্ড একদম কিছু দেখা যাচ্ছে না।
বোর্ডে দেখা যাচ্ছে না?
না স্যার, খুব আবঝা, মানে কিচ্ছু বোঝা যাচ্ছে না আপনি যেটা বোর্ডে লিখছেন।
এবার দেখা যাচ্ছে?
না স্যার, এখন তো বোর্ডের উপর মানে আলো পড়েছে, আরই দেখা আবঝা।
এবার দেখা যাচ্ছে? হ্যালো?
না স্যার, মানে আগের থেকে একটু পরিষ্কার
বোর্ডটা পুরোটাই দেখা যাচ্ছে, বোর্ডটা আউট অফ ফোকাস আর কি।
এবার
না হয়নি, একটু ডিসটেন্সটা কমাতে হবে বোর্ড আর ক্যামেরার মধ্যে।
ডিসটেন্স, আমার তো ডিসটেন্সটা এখানে ফিক্সড হয়ে গেছে।
আচ্ছা প্রফেসর এম সাহা, আমি একটা সাজেশন দিতে পারি। ঠিক আছে, ডিজিট গুলোকে একটু বড় করে লেখা হোক, আমার মনে হয় তাহলে ওরা কমফোর্টেবল ফিল করবে।
ঠিক আছে,
যেমন ন্যাচারাল নাম্বারস এর সেটটা যেমন একটু বড় ডিজিট হয়েছে, তেমনি অ্যাডিশন গুলো একটু বড় বড় ডিজিটে লিখলে আমার মনে হয় বাচ্চারা বুঝতে পারবে। আমরা ধরে ফেলতে পারছি আমাদের সাবজেক্টটা জানা বলে, একটু ডিজিট গুলো বড় করলে আমার মনে হয় হয়ে যাবে। ওকে, থ্যাংক ইউ।
So we are in the platform set of natural numbers. Now is it clear, right?
শেয়ার লাইটটা জ্বেলে দিন, কারণ ওই লাইটটা রিফ্লেক্ট করছে।
ঠিক আছে?
ঠিক আছে স্যার, ঠিক আছে। ওকে,
এবার দেখা যাচ্ছে মোটামুটি আগের থেকে ভালো এসেছে।
Yes, আগের থেকে বেটার।
Okay, so set of natural numbers n. So for any given two natural numbers m and n, so one of the relations hold. So these relations do not hold simultaneously. That means for any two natural numbers m and n belongs to this either m equal to n, or m less than n, or n less than n. So either this or this or this. So n less than m means m is greater than n. So alternatively we can use this symbol, m greater than n. Right? So this is called the order relation. This is called the order relation. And this law is called the law of trichotomy. So this is called law of trichotomy. This is called, this type of the order called the law of trichotomy. Now is it clear here? Is it visible in the board? Now is it visible?
Better than previous.
Better.
Okay. Now, so this type of the relation, either n less than m or m less than n, this type of the relation is less than type relation is reflexive, transitive, but not symmetric. Reflexive means it is called this type of relation reflects this. If we use this type of relation, this n less or equals to m or n less or equals to n, this is called the reflexive relation. Or it is if we allow the equality sign, then it is called the reflexive relation. It is the property transitive relations, but it is not reflexive. But it is not symmetric. So you can check it. So laws of compatibility. What are the laws of compatibility? Laws of compatibility. So if A less or equals to B, then for any natural number C belongs to N, A plus C is less or equals to B plus C. Similarly, in case of the additions, in case of the multiplication, A into C is less or equals to B into C. This type of the relations are called the laws of compatibility. Now, what is the well ordering property or well ordering principle? That is, every non-empty subset well ordering principle. What is this? Every non-empty subset of the set of natural numbers has a least element. Right? Suppose if we take A is a subset of N, A is this subset of natural numbers. So in this in the set A, we must have a least element. That means there exists an element P belonging to A such that P is less or equals to N for all N belongs to A. So every non-empty subset of N has a least element. Suppose if we take A is a subset of N where A is non-empty, then least element means there exists an element P belonging to A such that P is less or equals to N for all N belonging to A. So now we shall show that the well ordering principle and the principle of mathematical inductions are equivalent. Well ordering principle and principle of mathematical induction is equivalent. How shall we see? Let's see. So that means what we said, well ordering principle implies principle of mathematical induction, and vice versa. That means principle of mathematical induction implies well ordering principle. So we know the definition of the well ordering principle. We know what is the principle of mathematical induction. So let's proceed how the equivalence comes. Now proof. I am just giving the outline of the proof. Let M be a set of natural numbers. Suppose we are given the well ordering principle holds. Now we shall show the principle of mathematical induction property holds. Right? Let M be a set of natural numbers. Such that one belongs to M. And whenever N belongs to M, N plus 1 belongs to M. Right? We have to prove the axiom 5. That is, axiom 5 is called the principle of mathematical. That means we have to prove that is M equal to N. So first we start that M is a set of natural numbers such that 1 belongs to M and N belongs to M, N plus 1 belonging to M. Now let us take capital F. Let capital F be the set of all those natural numbers which do not belong to N. F be the set of natural numbers which do not belong to N. That means if we take the set of natural numbers here and if the set is N, is a subset of set of natural numbers N, and F is a set that is the members of the elements of the F is not an element of M. That means F intersection, that means F intersection M equal to 5. That is F intersection F equal to 5 and F union M equal to N. So now we shall have to prove that principle of mathematical induction follows. That means M equal to N. That means in order to prove M equal to N, so we shall have to prove F equal to 5. So F equal to 5. If we can show that F equal to 5, then automatically it will be proved that M equal to N, and automatically principle of mathematical induction follows. So let's see. Already we are given that F union M equal to N and F intersection M equal to 5, right? Suppose we have to prove F equal to 5. To prove F equal to 5. Suppose F not equal to 5. Suppose F not equal to 5. Suppose F not equal to 5. So we shall prove it by contradiction, right? So if F not equal to 5 by the well-ordering principle, so every non-empty set has a list element. Every non-empty set has a list element. So there exists a list element. By well-ordering principle, what you see? By well-ordering principle, that F has a list element. So M is the list element. So M is the list element of what? M is the list element of F, right? So that means M is less or equal to N for all N belongs to F. For all N belongs to F, right? Now, 1 not equal to M. Why? Now 1 not equal to M. Because 1 belongs to N. Already we have assumed in the earlier stage, 1 belongs to M. Naturally, since F intersection M equal to 5, so naturally 1 does not belong to F. 1 does not belong to F, right? Right? And because if 1 belongs to M and M belongs to M belongs to F, and since F and M intersection have no intersection, so 1 does not belong to F, right? Since 1 does not belong to F, so 1 does not belong to F. What we see, as N is the least element of F, so naturally M minus 1 does not belong to F. Why? Because M minus 1 is less than M. So in that case, M minus 1 would be the least element. So, but we have assumed that M is the least element. So therefore, M minus 1 does not belong to F, right? So therefore, since M minus 1 does not belong to F, so what we see, that M minus 1 belongs to where? Where? M minus 1 belongs to M. M minus 1 belongs to M, right? Because here we have assumed N is the least element. So we can conclude that M minus 1 does not belong to F. If it so happens that M minus 1 belongs to M, in that case M minus 1 less than M. So it violates our assumption that M is the least element, because we are getting another least element, another smallest element, M minus 1. So in this case it contradicts our supposition. So therefore M minus 1 belongs to M. Now what we see? Now you see 1 belongs to M and M minus 1 belongs to M. By well-ordering principle, what we see? That is M minus 1 plus 1 belongs to M. That is M is equal to M, right? So this is the principle of mathematical induction, right? So if 1 belongs to M and M minus 1 belongs to M, so by axiom 5, M minus 1 plus 1 is equal to M belongs to M. So therefore, in that case, what we see? What we see? So by completeness properties, what we see? So by assumption of the well-ordering principle, that which is not so, that M belongs to M. M minus 1 plus 1, because we see M belongs to M, but we have assumed that M is the least element of F. Then it contradicts. This M belongs to F. And here we are obtained M belongs to M, but F intersection M is equal to 5. So this contradicts. So contradiction arises due to the fact that F not equal to 5. So therefore F must be equal to 5. Since F is equal to 5, so M is equal to M. So therefore the principle of mathematical induction follows. Okay, so is it clear? So one part is clear. Hello, my dear students, is this part clear?
Okay, carry on. Thank you.
Okay. So next, now we shall see the reverse part. That is, the principle of mathematical induction implies the well-ordering principle, right? There is principle of mathematical induction, principle of mathematical induction implies well-ordering principle. Well-ordering principle. So how it comes? Suppose, so that means every non-empty set has a least element. So let us take A be a non-empty set of the set of natural numbers, and to prove that A has a least element. Suppose A does not have any least element. Suppose A does not have any least element. Also is proven by the contradiction way. So suppose A has no least element. Because we have to prove well-ordering principle. We have to show that the well-ordering principle holds. That means A has no least element. Okay. Right. Now let us construct a set M. Let us construct a set M, collection of all natural numbers. This such that X is less than A for each A. For each A belongs to A. For each A belongs to A. Now so M is the set collection of natural numbers for which X is less than A, for each A belongs to. So what we see, that means every element of A is greater than or equals to each element of M, or equals to. So every element of A is greater than or equals to each element of M, right? Right. Now, by the well-ordering principle, but you see M intersection A equal to 5. M intersection A equal to 5. Why? If M intersection A not equal to 5, let us take an element X belongs to M intersection A. That means X is equal to M. X belongs to M. That means X is equal to M. For some M belongs to M, and X is equal to A for some A belongs to A. That means X is equal to A for some A. So what we say? M is equal to A. Right? If M is equal to A, right? But here M belongs to capital M, but what is the property? That is M less than A. Because M is taken from M and A is taken from A. So by this relation, M less than A. But by the law of the trichotomy, one the relation source, either M less than A or M equal to A. So therefore, in that case, already we have assumed that M less than A. So therefore, M equal to A contradicts our supposition. So therefore, M intersection A must be equal to 5. Suppose M intersection A equal to 5. Now, so what we see? So M intersection A equal to 5. So now 1 does not belongs to A. Now 1 does not belongs to A. Why? If 1 belongs to A, then 1 will be the least, because 1 is the least element of the natural numbers. But already we have assumed that A has no least element, so therefore we claim that 1 does not belong to A, right? And also 1 does not belong to A. Also, what you see, 1 less than A, right? Since otherwise 1 does not belong to A, what does it mean? For each N, and A has no least element, 1 does not belongs to A. That means already we have assumed that M intersection A equal to 5. 1 does not belong to A, so therefore 1 belongs to M. So by the construction of the set M, so 1 less than A. Okay. Now assume P belongs to A. P belongs to M. So naturally P plus 1 does not belongs to A. And why? Because we know that P is less than P plus 1. P is less than P plus 1. So in that case, P will be the least element. But it contradicts our supposition that A has no least element. So P plus 1 does not belong to A. So what we see, that is P plus 1 belongs to M. So P belongs to M and P plus 1 belongs to this belongs to M. So by the principle of the mathematical induction, what we see that M is equal to N. So what we see, M is equal to N. Already we have seen that M intersection A equal to 5. So therefore N intersection A equal to 5. So it is possible only when A equal to 5. This is again contradiction, because already we have seen that, already we have assumed that A is a non-empty set. So this contradicts. So therefore, principle of mathematical induction again follows the Euler principle. So there is an equivalence part between the same property of the Euler principle and the principle of mathematical induction. Now, similarly, we can define the subtraction and division of n. So suppose subtraction means, already we have seen, suppose if we say that there is an order relation for any two natural numbers m less than n, so there must exist a natural number p belongs to a n such that m plus p equal to n. So therefore p is equal to n minus n. So this is the subtraction. Similarly, in a similar way, we can define the multiplication, right? So division. So it means m and n are two different natural numbers. We can find a natural number p such that m into p equal to n. That means p equal to n by m, right? Because this is meaningful, because division by 0 is meaningless. But we have started with the natural numbers, so m not equal to 0, so it's meaningful. So we can definitely a number. It may not be natural number, it may be a fraction, but after all, we are getting a number. That is m into p equal to this, so it divides n. So it is again a natural number, right? Now we shall come to the rational numbers. So what is the rational number? The number of the form p by q. The number of the form p by q, where p and q are integers and q not equal to 0, and GCD of p comma q is equal to 1. Right? So if p greater than 0, then we say that this set of all positive rationals. If p is less than 0, we say that set of all negative rational numbers. But always we shall assume that q not equal to 0, but q is greater than 0, right? So set of all positive rationals, for the sake of the simplicity, we shall take p is greater than 0, so that p by q is always positive, and it becomes a rational number. So it is the collection of the set of positive rational numbers. Similarly, in case of the negative rational numbers. Okay. Now, what are the fundamental properties of the set of the rational numbers? So I am not going into the details. Already you have seen in studying while your group theory or field theory, Q forms an ordered field. So if we take the set of the rational numbers, then field properties with respect to the additions, this closure property, associated property, with respect to the additions. Then there is an existence of the identity element, inverse element, commutative property also holds. Similarly, in case of the multiplication operations, closure property, associative property, existence of the identity element is one is the identity element for the multiplication identity element. Similarly, inverse is also there. Inverse existence of the inverse element. Similarly, commutative property also holds. So this is the field property structure of the field. And with respect to the addition and multiplication, all the properties also holds in case of the rational numbers. So also distributive property also holds in set of the real numbers, rational numbers. Now, order means that is two rational numbers can be ordered. Either if we take this is the x and y are two rational numbers, either x is less than y, or x is equal to y, or x is greater than y. So one of the relations also hold. So Q is unbounded. So I shall define what is a bounded set or what is the unbounded set, right? Least upper bound property. So I shall discuss later on. Then similarly, you see, whenever it comes, so I shall define. So a set, in case of this, in case of the rational number, a set is bounded. A set is bounded above if there exists a real rational number, okay, b, such that x is less or equals to b. Suppose a set S is a subset of, suppose S is a subset of rational numbers. So a rational number b belongs to Q is said to be an upper bound of the set of the elements in S if for all x less or equals to b holds, and b is called the upper bound, right? So among the all upper bounds we can get the least upper bound. So this least upper bound is called the supremum of the set S, right? So sup of S. So if the least upper bound, if the greatest bound exists in the set of S, then in that case, the greatest element is the supremum of the set S exists. There is the greatest element exists. Okay. Now, similarly, Q is dense. Means suppose if we take A and B are two rationals, so A less than B, how do you prove the dense property? I am not going in the topological properties. Dense property A bar equal to whole set. I am not going in the details. So it is the case of topological properties. Now A less than B. So if we take A plus then adding A plus A less than B plus A. So what we see, that is 2A is less than A plus B. That is A is less than A plus B by 2. So again, what we see that is A less than B. So A plus B is less than what happens? So B plus B, that is implies A plus B by 2 is less than B, right? So what we see that A is less than A plus B by 2, again less than B. So between two different rationals, we can get another rational, because if A is a rational, B is a rational, by the closure property A plus B is also rational, so A plus B by 2 is again rational. So between two rationals, we can get another rational. So if we take another, so A plus B by 2 equal to C. So between A and C, we can get another rational number. So we get C and D, we get another rational number. So between two different rational numbers, we can get an infinite numbers of the rational numbers. So in that case, we say that the rational numbers are dense. So there is set of the rational number is dense. Set of the rational number is also Archimedean property. Is Archimedean. Archimedean means suppose if x and y are two rational numbers and x is greater than 0, then there exists a natural number n such that nx is greater than y. So this is called the Archimedean property of the set of rational numbers. So if the time permits, I shall prove it. Similarly, Q is a countable set. That means, what is a countable set? That means there is 1 correspondence with the set of the natural numbers. So we can collect the set of rational numbers with the correspondence with the set of natural numbers. So that's why it is called set of rational numbers is a countable set, right? Similarly, Q is not a complete ordered field. That means the set of all rational numbers is a ordered field, but it is not complete in the sense the set of rational number has no least upper bound. Right? So that's why set of all rational numbers is not order complete, while the set of the real numbers is order complete. So if the time permits, then I shall show it. Okay. Now, you see, already we have shown that Q is dense. Now Q is Archimedean. What happened? How shall I show? So suppose A and B are two positive rational numbers such that A is less than B. Then there exists a natural number n such that Na is greater than B. Suppose this does not hold. That means Na is less or equals to B. Suppose Na is less or equals to B. Now multiply both sides. That is Na, B, because B is positive. Right? So Na into B inverse is less or equal to B into B inverse is equal to 1. So what happened? So N into A into B inverse less or equals to 1. Right? So this inverse 1 is again less than M, because any natural number M is greater than 1. So N into AB inverse less than M. This implies N by M less or equals to A by B. So what we see that any rational number is less or equals to A by B. It is not possible. If we increase the value of n for sufficiently large values of n, this does not hold that it is always less or equals to fixed quantity. So therefore, we cannot get that any rational number is always less or equals to A by B. So therefore, this thus we added a contradiction. Contradiction arises due to the fact that Na is less or equals to B. So therefore, Na must be greater than B. So this is called the Archimedean property, right? So we know that from the childhood days that every rational number is either terminating either terminating or recurring or non-terminating, right? Whenever it is terminating, so it is called the real rational number. Whenever it is not terminating, it is called the irrational number. So Q is a countable set. We know that because there is a 1-1 correspondence. If we take, suppose P and Q are rational numbers. Suppose P by Q is rational number. We take order pair P and Q. Now, how shall we find the 1-1 corresponding to the natural number? That means P plus Q, right? P plus Q. We shall construct. That is 1 by 1. This 1 by 1. Similarly, 1 by 2, 1 by this, 2 by 1. These are the rational number. Similarly, what happens? 1 by 3, 2 by 2, and 3 by 1. So this corresponds to a first correspondence, right? 1. Right. Similarly, this correspondence. How the correspondence this? The P plus Q. How will you define P plus Q equal to 2? 1 plus 1 equal to 2. Similarly, here P plus Q equal to 3. 1 plus 2 equal to 3. 2 plus 1 equal to 3. 1 plus 3 equal to 1 plus this 2 equal to 3. 1 by 3 equal to P. This P plus Q equal to 4. 2 plus 2 equal to 4. 3 plus 1 equal to 4. Here P plus Q equal to 4. But you see, 2 by 2 equal to 1. That 1 comes. So we discard it. So this is the first natural number. So 1 by 1 first number. This is the second number. This is the third number. This is the fourth number. This is the fifth number. So it corresponds to 1. So this corresponds to 2. This corresponds to 3. This corresponds to 4. This corresponds to 5. So there is a 1-1 corresponding between the set of the natural numbers. So therefore we can say that the Q is a countable set. So what you said, now geometrical interpretation. So what you see that geometrical interpretation for every rational number we can take a point. For every rational, suppose it is a directed line. So suppose it is starting from the 0 and it is a 1. So there is this is a P is a point. So OP is the length equal to P, right? OP is the length of P. So you see, this point P corresponds the number P. So what we see, that corresponding to the rational number, there exists a point P. But the converse is not true. Corresponding to point P, that doesn't mean that must exist a rational number. Because you see this figure, suppose it is 1, it is 1. It is 2. So this line and this line are same. If we take that is OAB and OB equal to C, and if we take AC equal to OB, then root 2. So you see what we see, the root 2 is not a rational number. So what we see that this point, root 2 means that means this is the line segment. So corresponding to the point, corresponding to the point, this is length root 2, corresponding to the point which is C, it does not mean that it is a rational number. So therefore, for every rational number, there corresponds a point on the directed line, but for every point on the directed that does not exist, that doesn't mean that must exist a rational number. So there is the geometrical interpretation of a rational number and a point. So already we have seen that need for the extension of rational number, because rational numbers are terminating. That means recurring decimal. Recurring decimals are called the real decimal number. Non-terminating decimals, rational numbers are called the non-recurring decimals. So rational number can be represented as by a point on a directed line, but the converse is not true. Already I have mentioned the totality of all points. The totality of all points on a line form. Totality of all points on a line are called the linear continuum or geometrical continuum, and the totality of all rational numbers are called the arithmetic continuum. So this is called the arithmetic continuum and general linear arithmetic continuum and linear continuum or geometrical continuum. Because it is called geometrical continuum because it represents the points on a line. So that's why called the linear continuum. And we know that corresponding to the rational number, there is a point. So therefore, the rational numbers are called the arithmetic continuum. The set consisting of all the rational numbers called the arithmetic continuum. So we all know that that is the x square is equal to 2. This equation does not satisfy by the rational number. We know that x is equal to root over 2 is not a rational number. So therefore, x square minus 2 equal to 0 is not satisfied by any rational root, right? Similarly, there is no positive integer n other than a square number has a square in the system of the rational numbers, right? So we can show that there is no positive integer n other than a square number has a square root within the system of the rational numbers. Okay. Shall I continue?
Yes, sir. Yes, sir.
So is it understood? Is there any up to this? Is there any question from the students?
Sir, yes, there is one or two. You may answer those questions after the talk.
Okay. Now I am coming to the set of real number system. Okay. So first we have started with the natural numbers. Then we have started with the rational numbers and some of the properties. Then we are coming to the set of real numbers. So in the case of the real numbers, the field axioms are also satisfied. That is additive property, additively abelian group, multiplicatively group, and there is non-zero elements has an inverse, and also the completeness axioms, that is least upper bound property, also satisfied, right? And in addition to that, distributive property also holds in the field structures. And also laws of trichotomy, there is either any two for any two types of the for any two real numbers, either x less than y or x equal to y or x greater than or to y. Similarly, compatibility relation also holds, right? See, already we have defined the upper bound, least upper bound. So similarly, we can say that the greatest lower bound also. Okay. So definition of a least upper bound. What is the least upper bound? That is, S be this, suppose R is the set of real numbers, S be a subset of the real number, subset of real number. A real number M is called the least upper bound if it has the following property. A real number M belongs to R is said to be the least upper bound if the following two properties holds. Number 1 and 2. So M is an upper bound of S. That means for all elements, for all x belongs to S, x is less or equal to M. And for every epsilon greater than 0, and for every epsilon greater than 0, there exists an element y belongs to M such that y is greater than M minus epsilon. Right? So that means that any number M dash less than M can be an upper bound of set S. So this is that means 2 and this notation are equivalent. So that means if M is the upper bound and if M dash less than M, we can say that M dash can never be an upper bound of this. That means for every epsilon greater than 0, there exists y belongs to M such that y is greater than M minus epsilon. And in that case, we shall say that M is equal to supremum of S. Right? Similarly, we can define the greatest lower bound. We can simply say the greatest lower bound. How? Now, suppose S is a subset of R, right? The small m is called the lower bound of S if for all x belongs to S, that means x is greater or equals to m, right? And m will be called the greatest lower bound if for every epsilon greater than 0, there exists an element y belongs to S such that y is less than m plus epsilon. If such 1 and 2 properties, first and second property holds, in case of the set S, then we say that M is the greatest lower bound, right? Right. Now, what is the least? What is the completeness property of the set of the real numbers, right? So we take it as a guaranteed proposition that every non-empty subset of real numbers which is bounded above has its supremum. Bounded above means that is whenever there exists a real number M such that x less or equals to m, that means for all x belongs to s, we say that this set is bounded above, and m is for the upper bound. Among all such upper bounds, m we can definitely get a least upper bound, right? And that least upper bound is called the supremum of the S. So that's why the axiom is known as the completeness axiom, and sometimes we say that LUB axiom, least upper bound axiom. So what is it? Now every non-empty subset of real numbers, which is bounded above has a least upper bound. Every non-empty subset of real numbers which is bounded above has a supremum. So with this assumptions, we can automatically prove that every non-empty subset of real number which is bounded below has the greatest lower bound. So if we take this assumption that is this is true, there is least upper bound axiom is true, that means completeness property is true, then automatically we can prove as a theorem that every non-empty set of real numbers which is bounded below has its greatest lower bound, right? So that means we have to prove that every non-empty subset, if S is not equal to 5, then every non-empty subset of S has a which is bounded below has a greatest lower bound. You see how greatest lower bound. How it comes. So construct a set is dashed. Suppose construct a set X belongs to R such that minus X belongs to S. You see S not given S not equal to 5, which is bounded below. We to prove it has a greatest lower bound, right? Under the assumption, the axiom is true, that is the every non-empty subset of R which is bounded above has a least upper bound, right? Since S is bounded below, so S has a lower bound because already assumption is given that S is bounded below, right? So S has a least upper bound, right? So therefore S has a least upper bound. That means whenever X belongs to S dash, then minus S dash minus X belongs to S. Since S is bounded below, therefore minus X, there is a real number K, that the minus X is greater or equals to K. That means this implies X is less or equals to minus K, right? That X belongs to S dash. That means S is bounded above by the assumption that every non-empty set which is bounded above has a least upper bound, right? So by the assumption there is the least upper bound property axiom, there is a supremum F such that X is less or equals to M, right? For all X belongs to S, right? So therefore minus X is greater or equals to minus M, right? Minus X is greater or equals to minus M. That means here minus X belongs to S, right? So thus every member of S is greater or equals to, because minus S belongs to S, so we can say in language that every member of S is greater or equals to minus A. Also, since M is the least upper bound, M is the least upper bound of what? S dash. By the second axiom of the least bound property, there exists a member Y belongs to S dash such that Y is greater than M minus epsilon. So whenever Y is greater than M minus epsilon, so minus Y is less than minus M plus epsilon. Here minus Y belongs to where? Minus Y belongs to S. So what we see? Minus X belongs to S and minus Y get less than minus M plus epsilon. That means minus M is the greatest lower bound of S. So that I wanted to prove that every non-empty subset of real number which is bounded below has a greatest lower bound. So here minus M is the greatest lower bound. So therefore, the set of all rational numbers, by the truth assumption, the LUB axiom that every non-empty subset of S has a least upper bound, of the boundary has a least upper bound, then automatically you can prove the theorem that every non-empty subset S of R which is bounded below has a greatest lower bound. So also we can show that the set of rational numbers is not order complete. Why? So if you take suppose order complete means That means it does not have any least upper bound property. Order complete means set of all S. If you take X belongs to a Q such that X is greater than 0 and X square less than 2. So this set S does not have this set does not have any least upper bound property. So we can say that it is set of all rational numbers is not order complete. Now this set is non-empty because why? 1 belongs to Q, 1 is greater than 0 and 1 square is less than 2. So therefore S not equal to 5. So therefore S is bounded above. So we shall have to prove that S does not have any least upper bound property. So if so happen that S is least upper bound, then it will automatically be order complete. So our target is to show that S is not order complete. So if possible let it is order complete, that means it has a least upper bound. So if possible let there exists a rational number K such that K be the supremum. So therefore 0 less than X less or equals to K. K is the supremum value. Wherever K is greater than 0. Right? Because X is greater than 0, naturally K must be greater than 0. So by the law of the trichotomy, what we say, either K square is less than 2 or K square is equal to 2 or K square greater than 2. So one of the relations among the three relations also holds, right? K square, either K square less than 2, K square equal to 2 or K square greater than 2. So we shall discuss categorically one by one. So whenever K square less than 2, suppose K square less than 2, right? K square less than 2. Let us consider a rational number y equal to 4 plus 3k by 2 plus 3k. Naturally 2 plus 3k, sorry, it is 3 plus 2k. Take 4 plus 3k, 3 plus 2k. Where k greater than 0. You see y is greater than 0, right? Y is greater than 0. Right, now calculate k minus y. K minus y means that is k minus 4 plus 3k by 3 plus 2k. So that will be calculated as 2 into k square minus 2 by 3 plus 2k. So what we see, first case, if k square less than 2, so it is less than 0. So what we see, that is k minus y less than 0. That means k is less than y. Okay, so therefore k is less than y. That means y is greater than k. Y is greater than k. Now again you calculate 2 minus y square. Again 2 minus y square equal to 2 minus 4 plus 3k by 3 plus 2k whole square, right? So it will give as 2, this cancel out. So 2 minus k square by 3 plus 2k square, 3 plus 2k whole square. This is again less than 0. So what we say, that is 2 minus y square is less than 0. That means y square. So what we see, that is 2 minus y square. That means, sorry, this will greater than 0. So 2 minus k square. 2 minus k is greater than 0. 2 minus k square greater than 0. So therefore 2 minus y square greater than 0 means greater than 0. So therefore y square 2 minus y square greater than 0. So y square less than 2. So therefore what we say is y belongs to S. Now y belongs to S. Now you see y is greater than k. You see y is greater than k, and you see y square less than 2. Already we have assumed that k is the least upper bound. K is least upper bound. So we can take we see that there is an element y belongs to x such that y is greater than k. So it violates that k is an upper bound. So therefore in that case k square less than 2, this set has no least upper bound. Similarly, if we say k square is equal to 2, k square is equal to 2, that means k is equal to root 2. So you see k is a rational number, but root 2 is an irrational number. So again it violates. So again if we see that k square is greater than 2, again we can see similarly that there exists an element y belongs to S such that that it is not the least upper bound. So therefore set of all rational numbers is not order complete. So similarly, Archimedean properties also hold in the case of the real number. That is, if xy belongs to R and x is greater than 0, then there exists a positive region n such that nx is greater than y. Right? So I am not going into this. Already it has been shown in case of the real numbers. So I am not going into these details. So some important deductions from the Archimedean property. If x is greater than 0, and then there exists a natural number y, such that for any y belongs to R, that suppose nx is greater than y. Now, if y greater than 0, then there exists n belongs to n, such that n is greater than x. How it comes? If we take x equal to 1, that is x is equal to 1, that is 1 is greater than 0 by the Archimedean property n into 1 greater than y. So therefore n is greater than y, right? Similarly, for any two real numbers x less than y, we can find a natural number n such that ns, suppose for any real number x greater than 0, there exists a natural number n such that nx is greater than 1. So these are the important deductions, and this can be deduced from the Archimedean property. So similarly, set of all real numbers have a dense property. Then between any two real numbers, there exist infinite numbers of the real numbers. So either it may be a real rational number or it may be a real irrational numbers, right? So that's why, in the sense, is called the dense property. So similarly, we can take that every real number can be represented as a decimal number can be represented. That is, any real number any real number can, suppose a real number 5 point, suppose any real number can be represented as a non-terminating decimals or non-terminating decimals. In that case, it's a recurring representations of the number systems, and similarly non-recurring system in the real number system. Okay, non-recurring representation.
Sir?
So geometrical interpretation, or again, so what that is a main drawback in the case of the real numbers. So corresponding to rational number, there is a point, but the converse was not true. But in case of the real numbers, there is a 1-1 correspondence between the set of the real numbers and point. So whenever there is a real number, we can get a point. That point refers to either real rational number or real irrational number. Similarly, corresponding to the real rational number or real irrational number, we can definitely get a point on the directed line. So there is a 1-1 correspondence between the set of real numbers and the set of points. So collection of all the points, real numbers, is called the arithmetic continuum, and similarly the set of all real numbers on directed line are called the linear continuum and geometrical continuum. Okay.
Sir, may we take some doubts?
Yes. So one thing I would like to say, so a set of all, similarly what we see that the set of rational numbers are countable, right? But in case of the real numbers, it is not countable, right? So because it can be shown. Already you have shown the proof in any textbook. So I'm not going into it because time is very short. So with this, I now stop here. So may I invite some questions? Is there any question from the students?
Yes, sir. After shortlisting all doubts according to the relevancy, there are some questions from the students.
Yes.
First one is by Shubhendu Kaur. He is asking about MP equals to N always.
What is N?
MP is equals to N.
M into P
is equals to N always.
Here P is a natural number.
Shubhendu, if you are listening, then please you may state, you are asking to state your doubt in front of sir.
Yes, ma'am.
Yes.
Sir,
Already, if for any, suppose you are given, suppose M is less than N and N divides M, for the case of natural numbers. If M is less than N and N divides N, in that case, there exists a natural number. There must be a natural number P such that MP equal to N.
Yes, sir. That was my question, because you did not mention M divides N, etc.
Yes, already yes. Already M is less than N, and already I have in mind that in some stages I have told that N must be divisible by N.
Okay, Shubhendu. Next one is Tajinder Sangroha. He is asking about well ordering principle and principle of mathematical induction are equivalent.
Yes. Already I have shown it.
But
Well
there
ordering-
is any proof of them individual being to get true.
Yes, already I
There
have
is
shown
no
it.
proof.
Already I have
Yes,
shown
that
this
is
well ordering
already
principle.
already.
A well ordering principle implies the principle of mathematical induction. Again, principle of mathematical implies well ordering principle. So these proofs
Yes,
are
sir.
shown by the method of contradiction. Already shown. These equivalent parts are already shown by the method of contradictions. Already in the initial stages, already whenever well ordering principle is there, there is a state construction by set F. That is F union M equal to N and F intersection M equal to phi. In that case, principle of mathematical induction follows. Similarly, in case of the reverse part, we have constructed a set capital M that is X less than A. So in that way, we have this is a constructive part. Already we have shown it.
Sir, there is a Krishanu Hayat. Whenever we divide 1 by 2, there is Krishanu Hayat. Listening, Krishanu Hayat. Am I audible to you? Please ask your question to sir.
Hello, Krishanu. Hello, Krishanu.
Yes, sir.
What's the question?
Whenever in real numbers, 1 divided by 2 is equal to the half and half.
Okay,
Yes,
Krishanu,
sir.
okay. Your network is
Yeah,
really
your
down.
network is very feeble. Please write your question in a chat box. That will be very
Sir,
clear to me.
Jyoti, can you
Sir,
read the question?
Yes.
Please already
Whenever
read
we
it.
divide 1 by 2, the question is whenever we divide 1 by 2, we 2 equal parts of 1. Similarly, 1 is divided by 3 gives 3 equal parts of 1. Then we can say that dividing a small number by a large number makes equal parts of small number in number
Yes.
of large number. Everything the parts are getting smaller as respect to the larger number. In this
Yes.
way, can we say infinity is the smallest and 0 is the largest number in real numbers because the number divided by 0 is infinite?
Actually, if we say that but infinity is not a number. Infinity is a symbol. Infinity is not a symbol. Infinity is not a number. Just infinity is a symbol. So whenever any number cannot be fixed, whenever any number can be measured, so that is how is possible either heavy large quantity. So it is very fictitious term. So that's why we said use the term infinity. So in that case, infinity cannot be treated as a number.
Yes, sir. Very nice explanation, sir.
Right. Infinity is not a number. Infinity is just a symbol.
Yes, sir. Infinity is only a symbol.
Symbol.
Thank you. Thank you very, very much, sir, for this valuable and enriching speech and your guidance and support towards us. Thank you very much. Sir.
Thank you.
Yes, sir. Are you listening?
Okay, I'm listening. So is there any question from the other students? Tajinder Sanghura, you provided the principle of mathematical induction and well ordering principle are equivalent, but how can we prove that both are individually true? Actually, well ordering principle is an axioms. Similarly, principle of mathematical is an axioms. So two axioms, whenever axioms, so if I say that from a point, infinite numbers of the straight lines can be drawn. So it is an axioms, or you can prove it. So it is an axioms. So well ordering principle is an axioms. Similarly, principle of mathematical inductions is an axiom. So two axioms are equivalent. So axioms may be either proved or axiom may not be proved. So whenever we have to develop a subject, the subject is based on the axiom. So that's why it is very much important to develop the subject under the assumptions of the axioms. So two axioms are equivalent.
Any question?
So you see, well ordering principle, every non-empty set, if we arrange the elements, you can definitely in any sequential manner, so you can get a list element. So by intuition property. So it cannot be proved. But whenever it is under the assumption it is true, so you can also prove the principle of mathematical induction. So is it clear? Kishanu, sir, what is E and from where it comes? So E. See, E is an irrational number. Hello. So
Yes,
because
sir.
it is not terminating. So rational numbers are terminating or recurring. So in that case, whenever E is, because E means E equal to 1 plus 1 by factorial 1, 1 by factorial 2, 1 by 1 factorial 3, and so on. It is a series. It can be never ended. So it is a series.
Okay.
So it is non-terminating. Right, whenever you see e to the power x, right, e to the power x means 1 plus x by factorial 1, x square by factorial 2, and so on. So e to the power 1 equal to 1 plus 1 by factorial 1 by factorial 2, and so on. This is a series. So you see, so it is approximately equals to 2. We denote this series exactly equal to, but it can never be terminated. So how can you say it is a rational number? So rational numbers are two types. Either it may be recurring or it may be terminating. Is it clear?
Yes, sir. Due to lack of time, we are not including many more doubts. And on behalf of our family of Fakir College, we are thanking you, sir. Thanks to you very much for this enriching and valuable speech. Our students and we all are benefited by this lecture.
Okay.
Thank you very much, sir.
Thank you. So let me stop here.
Yes, sir. So our second and last speaker is respected Professor Manjusha Majumdar Madam. Professor Manjusha Majumdar Madam is a former professor of Department of Pure Mathematics in University of Kolkata. She is also serving as an eminent lecturer of PG section of our college. She has a large number of publications in various reputed journals. The fields like differential geometry, Riemannian geometry, general relativity are enriching by her work. Today, her topic of discussion is on curve and surface. I cordially request you, ma'am, for your flourishing talk. Ma'am, please.
Okay, thank you very much. Actually, first of all, I must thank my organizer for conducting this program and inviting me again. Hope you know, most of the participants and also the faculties, that this lecture is a continuation of my previous lecture, which I delivered in the last month. And in the first lecture, we have introduced the concept tensor, which is one of the powerful concepts for studying differential geometry. And this approach has been introduced in our UG course of the University of Calcutta. And today, I have taken the topic as curves and surfaces, but this should be explained in the light of tensor, because it is my intention also, and I think the intention of the organizer also, to say a little bit on this topic in the light of tensor. Actually, this concept can be treated through school level, through college level, and through university level also, because this curves, differential geometry of curves and surfaces, is very much in the first semester of the University of Calcutta PG course. And there we study this concept in the light of vector. Then you may ask me the question, then why we are studying this concept in the light of tensor? So for this particular question, let me explain for this reason we have chosen in the undergraduate level for just for 1 or 2 minutes. Then, of course, I will come to my topic. Actually, you know, the tensor concept, which I explained in my first lecture, has a wide application not only for studying the geometry, but also in physics. And if you want to study the cosmology and also the special theory of relativity, which is also taught in the special paper of mathematics, mainly in the, and of course in the physics, you have to know tensor because it is the building block. If I say that I do not know A, B, C, D, E, F, G, H, then I cannot study English because it is the building block. And that's why our intention, and also from the point of view of the management of the University of Calcutta, that we will offer this subject not as a particular subject, as a special paper, but as an optional. Because, you know, geometry, not every student will go to the physics, because there are many participants who have many interest in other subjects. That's why it's not a core paper, but a just elective paper. Those who are interested can opt for it or not. And my intention for today's lecture is that the continuation of the concept as I deduced earlier in my first lecture. Moreover, this webinar, so far as I know, it is absolutely for the state level participants from the different colleges. And hence, I wish to deliver my lecture mostly in the language Bengali. If there is any problem to understand, you just send me your comments in the chat box and I will immediately switch over to the English language. But I can say that it has been announced as a state webinar, and that's why I am going to define, or I am going to explain in the language Bengali. Okay? Fine.
Madam, can you please fix your camera because your face is totally not visible.
Do you need to see my face, Shantanu?
Yes, ma'am.
Okay. I don't think so that you need to see my face. Okay. Just forget about my face. You just concentrate on the topics. Okay, Shantanu? Acha. Okay. And let me start my talk. Curve and surfaces. Okay? আমি যখনই ধরো তোমাদেরকে বলবো যে কার্ভ বলতে তুমি কি বোঝো বা কি ভাবছো তুমি, অনেকে স্ট্রেট লাইন আঁকবে, যদিও এটা আমরা কার্ভ বলি না, পরে আসছি। কেউ আঁকবে প্যারাবোলা, কেউ আঁকবে সার্কেল। যার যেরকম ইচ্ছে সে সেরকম একটা ছবি খাতায় এঁকে নেবে। তাহলে আমি কার্ভ কাকে বলবো? ফার্স্ট অফ অল, স্ট্রেট লাইন যারা আঁকছো, ইন দ্য স্পিরিট অফ জিওমেট্রি আমরা ওটাকে কার্ভ বলি না বা বলবো না। কেন বলবো না সেটা আমি পরে এক্সপ্লেইন করব। কিন্তু আগে আমি বলি, এই যে ভ্যারাইটি অফ স্টুডেন্টস ইন দ্য ক্লাস, ভ্যারাইটি অফ পিকচার্স আমরা পাই ক্লাসে, এটাকে যদি আমি বলি যে এতগুলো ছবি, এতগুলো জিনিস আমি একটা লাইনে এক্সপ্লেইন করব, তখন জিওমেটাররা বলেন যে ওয়েল, তুমি যেটা ছবিটা এঁকেছো, we can think that these figures have been drawn in a space of dimension 2, যেটা আমরা নোটেশনে বলি R2, এবং ম্যাথমেটিক্যালি আমি বলবো যে আমি এটাকে লিখবো f of xy equal to c, constant. xy what? xy means যে তুমি যে ফিগারটা এঁকেছো তার উপরে যদি আমি একটা কোনো পয়েন্ট ভাবি, সেই পয়েন্টের কোঅর্ডিনেটকে আমি ভাবতে পারি xy. ওকে? Now if you go to the space of dimension 3 or 3, এটাকেও তখন আমরা ওই জাতীয় একটা কিছু ইকুয়েশন লিখি বা লিখবো, কিন্তু এই যে অ্যাপ্রোচটা f of xy equal to some constant, এটা একটা নাম আছে, এগুলোকে বলা হয় লেভেল সারফেস বা লেভেল ইকুয়েশন। কিন্তু এই অ্যাপ্রোচে এগোনো বা এই অ্যাপ্রোচে টেন্সারে কনসেপ্টে এগোনো ইজ নট অ্যাট অল পসিবল। আমি গোড়াতেই বলেছি যে আই উইল এক্সপ্লেইন দ্য কার্ভস অ্যান্ড সারফেসেস ইন দ্য স্পিরিট অফ টেন্সার। কাজেই I will stick to the definition of the curve as given by all-time famous mathematician Gauss. তিনি কি বলেছিলেন? তিনি বলেছিলেন যে ওয়েল, তুমি যদি কোনো কার্ভকে ডিফাইন করতে চাও, যে জিওমেট্রিক্যাল এন্টিটিটাকে আমি বলবো কার্ভ, আমি ম্যাথমেটিক্যালি এইভাবে লিখবো যে all points, the totality of points whose coordinates are function of a single parameter. Beautiful definition. Mathematically আমরা লিখি xi equal to xit. T means parameter, I means তুমি যতগুলো ডাইমেনশন নিতে চাইছো বা যেভাবে ভাবছো, তার মানে এই ডেফিনেশনের পাওয়ারটা কিন্তু অনেক অনেক বেশি। অর্থাৎ আমরা আন্ডার গ্রাজুয়েটে বা স্কুল লেভেলে যখন পড়াই, আমরা মুখে উচ্চারণ করি না প্রথম দিকে ডাইমেনশন, স্কুলে তো বলিই না, হাই স্কুলেও বলি না, কিন্তু আমাদের সাবকনশিয়াস মাইন্ডে জিওমেট্রি আমরা পড়াই R2-তে। খানিকটা কলেজে এসে আমরা সাবকনশিয়াস মাইন্ডটাকে একটু বার করে নিয়ে আমরা R3 বলি। কিন্তু তুমি লক্ষ্য করে দেখো, যখনই আমরা R3-তে যাই, তুমি যে ছবি আঁকতে চাও না কেন, whether it is on your plain paper or whether it is on your blackboard, আমরা থার্ড লাইনটাকে ডটেড আঁকি। কেন আঁকি? তার কারণ আবার সেই জিওমেট্রি, তোমার খাতা এবং তোমার বোর্ড, এটা কিন্তু ডাইমেনশন n equal to 2। ইনফ্যাক্ট আমরা যে পৃথিবীতে বাস করি, দ্য স্পেস, তারও ডাইমেনশন 3, n equal to 3। You just look at your room. আমরা এবার অ্যালজেব্রাইক স্টাইলে যদি বলি, তিনটে মিউচুয়ালি দেখো পারপেন্ডিকুলার লাইনস, লেংথ, ব্রেডথ, হাইট। অ্যালজেব্রাইক্যালি এই কথাটা আমরা বলি না, কনসেপ্ট এক, কিন্তু অ্যালজেব্রাতে আমরা বলি দে আর দ্য বেস, বেসিক্স। সেই কনসেপ্টটা আমরা পড়াই ভেক্টর স্পেসে, অ্যাবস্ট্রাক্ট কনসেপ্ট আমরা বলি। তার কারণ আমরা যা কিছু দেখি বা দেখাই, যেটা জিওমেট্রির মেইন পার্ট, পিক্টোরিয়াল এফেক্ট, সেটা আমরা n equal to 3-এর বাইরে পারবোই না। তাহলে n equal to 3-এর বাইরে কি আমি যেতে পারবো না? অর্থাৎ এই স্পেসের বাইরে কি আমি যেতে পারবো না? অফকোর্স আমরা যেতে পারবো, কিন্তু সেখানে জিওমেট্রিটা আমরা পড়বো বা ভাববো কনসেপচুয়ালি এবং ম্যাচিউরড ব্রেইন দিয়ে। সেই জন্য টেন্সারের এই কনসেপ্টটা is very, very powerful. Let us go back to our original definition of curve as given by Gauss. আমি লিখছি xi equal to xit. T what T? T is nothing but the parameter. কেন প্যারামিটার? আমার দরকার কি নেওয়ার? এইখানেই উত্তরটা আমরা টেন্সারে পাবো। You just recall, আমরা যখন আন্ডারগ্রাজুয়েটে টেন্সার, ভেক্টর, ট্যানজেন্ট ভেক্টর ইত্যাদিগুলো যখন আমরা বলি, বা ভেলোসিটি ভেক্টরও যখন আমরা বলি এটসেট্রা, আমরা কিন্তু ডিফারেন্সিয়েট করি কোনো ফাংশনকে, অর্থাৎ dy dx এটসেট্রা এটসেট্রা ম্যাথমেটিক্যালি করি। ফিজিসিস্টরা ওই কনসেপ্টটাকে বলেন ভেলোসিটি ভেক্টর, আমরা জিওমেটররা সেটাকেই বলি ট্যানজেন্ট ভেক্টর। তাহলে ডাইমেনশন অফ দ্য স্পেস সেটা যেমন ভাইটাল, তেমনি আমি কোন অপারেশন করে আমি ট্যানজেন্ট ভেক্টরের কনসেপ্টটা দিচ্ছি, সেটাও কিন্তু সাইমালটেনিয়াসলি অসম্ভব পাওয়ারফুল। কিন্তু আন্ডার গ্রাজুয়েটে আমরা এগুলো উচ্চারণ করি না, আমার দরকার নেই। তাহলে আজকে আমরা যে কার্ভস ফার্স্ট ডিফাইন করব, আমার undergraduate আমার underlying যে স্পেসটা, it is not the Euclidean space of dimension 3, but we will choose the space to be Riemannian space of dimension n. Why? Because it is nothing but the definition of a higher dimension which can be visualized when I will put n equal to 3, and it will automatically go to the Euclidean space where we do live or stay. So first of all, my answer is our space is now Riemannian space of dimension n. আমরা বেশিরভাগই ফাইনাইট ডাইমেনশনাল নিয়ে পড়ব, এবং আমরা ফাইনাইট ডাইমেনশনাল নিয়ে যখন ভেক্টর স্পেসও পড়িয়েছি, আন্ডারগ্রাজুয়েটের কনসেপ্টে আমরা ইনফাইনাইট ডাইমেনশনাল পড়াইনি. That is why I will stick to my lecture to finite dimensional. So the first question is over. We will concentrate mainly on Riemannian space of dimension n. Now, the operation, tangent vector, যে কনসেপ্টটা আমরা আন্ডারগ্রাজুয়েটে অ্যানালিসিসে দিয়েছি, এবং this concept is also studied by Gauss, এবং এটাকে বলা হয় লোকাল ডিফারেন্সিয়াল জিওমেট্রি. কিভাবে করব? এই যে ডিফারেন্সিয়েশনটা যেটা আমরা আন্ডারগ্রাজুয়েটে পড়িয়েছি, টোটাল ডিফারেন্সিয়েশন, তাহলে I have to search for such type of differentiation in tensor also. And I have already introduced the concept of tensor in my first lecture. সেখানে আমি বলেছিলাম যে well, we have introduced, that is also a very powerful concept, algebra in a tensor, and we have shown the concept of tensor is such that we can form an algebra over it. Now, analysis part. Yes, we can introduce the analysis also on the tensor. Now, you just recall in analysis the differentiation, two types of differentiation. One is total differentiation, another is partial differentiation. For your kind information, these two types of tensor can be introduced, will be introduced in the tensor also, but mind that two types of tensor has been introduced in our undergraduate course when the dimension is n equal to 3. But here, the dimension is more than 3. So the research will be such that if I explain total differentiation, covariant differentiation, it will be such that whenever I will put n equal to 3, it will come up my natural total differentiation and covariant differentiation. The approach or the research is that I will stick to the total differentiation today because my topic is curves and surfaces, and to study the curve, the differentiation is known as intrinsic differentiation. What is the parameter? Parameter is the famous T, which has been given by Gauss. So, all the components or all the objects of the tensor can be differentiated with respect to the curve parameter, that is T. And there is an explanation, and there is an expression also mathematically, which I don't want to write down because, oh yes, Krishanu, I will give you your answer when r equal to 4. Let me go through in general, then I will come for n equal to 3, n equal to 4. Just wait for a few minutes, okay? So this type of concept is such that it can be defined in general, whatever be the dimension. That means 1, 2, 3, 4, ... n. And this notation can be seen from any book of tensor. But it has been defined in such a beautiful manner that something intrinsic differentiation of an object equal to total differentiation, some particle, some objects, part plus some objects together with Christoffel symbols. Why Christoffel symbols? I have already explained in my first lecture that Christoffel symbols are such that they depend upon the partial derivative of the metric coefficients whenever you are considering a space of dimension greater than 3. Why? Again, you come to the metric of our general Euclidean space. In the general Euclidean space, metric is such that you cannot come up with the fundamental metric tensor because the value is either 1 or 0. I can go through the metric of the Euclidean space. It is GSS square equal to dxi. That is, the coefficient of dxi is either 1 or 0. So how can you take the partial derivative of 1 and 0? So it will be 0. And that's why we cannot give the expression of Christoffel symbols in the Euclidean space. And that is the beauty of the tensor, that whenever you are considering the object in a space of dimension greater than 3, you are getting all these symbols. And you have to be very, very particular that these terms will come up while you are taking the differentiation with respect to the curve parameter. So I think that in a nutshell, the method of differentiation is more or less clear, that we have to introduce a new type of differentiation to study the curves and surfaces in tensor. The expression can be seen from any book. Let me clarify the concept. Now again, you come back to the figure of curve. You just forget about the straight line. You just draw a curve. You choose a point, particular point on your curve. You just think of a tangent vector as you draw in your undergraduate course. So, in most of the cases at this particular point, you can study locally, and that is why this approach, according to Gauss, is known as local differential geometry. Why? Because at that particular point, you just draw a tangent, okay? Again, we have taught in our undergraduate course that any line which is perpendicular to the tangent vector can be thought of normal. So at once you can draw a normal. In the blackboard also, teachers draw these two lines. But I have already told you the space where we do belong, it is the space of dimension n equal to 3. So according to algebra, or according to the concept of vector space, the basis, you must have 3. Now, you can think of tangent vector, normal vector as a basis, but where is third component? Third component is nothing but you just think of a pen or pencil or chalk at that particular point, which is such that it is perpendicular to the tangent and perpendicular to the normal also. In the blackboard, we draw that line as a dotted figure. In the exercise book, we also draw the line as a dotted figure. And in the book or in the theory, we call it as a binormal. So for every curve, for every point on that particular curve, you have a local basis, tangent, normal, binormal. It is absolutely important because whenever you have studied the vector space, if it is of dimension n, you have taught the number of elements in a basis vector has n components. So in this curve, the number of bases locally has 3, which is justified because of the dimension of the space. Now we want to study the curve. The main criteria to study the curve, the basic concept is curvature and torsion. Now, how can I give or how can I have the concept of curvature? It is the differentiation of these 3 vectors. And mind that in the vector space also, whenever we choose the standard basis, E1, E2, en, you think we write it as 1, 0, 0, 0, 0, 1, 0, 0, 0, etc. We don't utter the word length because length is the concept of geometry. In algebra, we just write 1, 0, 0, 0, 1, 0, dot, 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 dot. But in the geometry, we are concerned with the length also. And that length is the terminology in the geometry is unit vector. That means the length of tangent, the length of normal, the length of binormal, that is each and every vector is assumed to be unit vector. In the geometrical language, if the metric is gij, dxi, dxj, then the length of the vector, if I denote it by lambda as the tangent vector, normal vector mu, and the binormal as nu, all these symbols are the Greek symbols. Like English language, A, B, C, D, etc. In the Greek language, we write it as lambda, mu, nu. So, length of the vector lambda, that is gij, lambda I, lambda j equal to 1, so on. So this is the first criteria, but this is not new. But we don't utter this word. But actually, this is the concept which you have already studied in the algebra. It is the geometrical point of view that we say that it is the length of the each vector is 1. Fine. Now I have to take the differentiation of each unit vector. But again, I have to think that I am considering all this vector in a space whose metric is completely different from the Euclidean space, that is Riemannian space, which I have taught earlier in my first lecture. The differentiation with the tangent vector, that means the intrinsic differentiation of the tangent vector, to make it a unit vector, we will find after a few calculations a scalar quantity, and that scalar quantity is termed as curvature. Similarly, we can take the intrinsic differentiation of the normal vector, intrinsic differentiation of the binormal vector. Intrinsic differentiation of the binormal vector will give you the scalar quantity as torsion. And what about intrinsic differentiation of the principal normal or the normal? This also gives a relation of curvature and torsion, but in a linear combination of curvature and torsion. So forget about it. We have to concentrate now on curvature and torsion. What does it mean? I have already told you that these are nothing but some scalar quantity. If it is a scalar quantity, then you have the choice that it may be 0 or may not be 0. Yes. If the curvature is 0, that is denoted by kappa, and the torsion is denoted by tau. Again, the notation is from the Greek language. If the curvature kappa is 0, we define the curve to be straight line. Yes, I'm giving the answer of this question. Let me give the answer of the question of curvature at first. Thank you. Now the curvature, if it is equal to 0, we are calling it straight line. Now you can tell me, Joel, you are giving the definition. We are not at all interested. Give the geometrical interpretation, because if we are learning or we are teaching the subject geometry. Okay, just wait for a few seconds. Again, the curvature can be greater than 0. Yes, most of the curves are such that the curvature is positive. What about negative curvature? Does it exist? Of course it exists, but the space where we do belong, that is the Euclidean space, its curvature is 0, no mention. But whatever space, mainly the Riemannian manifold, whatever space we deal, at least to the undergraduate and also the postgraduate, we are concerned with the positive curvature. Negative curvature comes up, but it is another kind of geometry, which is known as hyperbolic geometry. This is not my topic of lecture today. So let us accept now that we will be concerned with either kappa equal to 0 or kappa is greater than 0. Now, what does it mean? I'm saying that if it is 0, then it is straight line. Actually, curvature, the meaning of the word curvature lies in the definition, curve, curvature. You just think of the straight line and you just think of any curve, say for parabola. Okay. If I say that what is the geometrical interpretation of curvature, you think at first parabola. You choose many of the tangent vector and its direction. And you will be surprised to think, or you will be surprised to draw that at every point, the direction of the tangent vector is not same. It's bending, or we are saying carved. But if you think of straight line, at every point, whenever you are drawing a tangent vector, it is along the straight line. So there is a basic difference between the direction of the tangent vector of the straight line and the direction of the tangent vector to any curve. For example, parabola. Here lies the definition. The bending of the tangent vector gives the curvature. In English, we say that curvature gives the extent, how much the curve is not contained in a straight line. In English language, it is very easy to define the geometrical interpretation that curvature measures the extent, how much your curve is not contained in the straight line. That means, trivially, straight line has been taken that curvature measures 0. তার মানে তুমি যে কার্ভটা ভাবছো সেই কার্ভটা তোমার স্ট্রেট লাইন থেকে কতটা বেন্ড করেছে, কতটা ঘুরে গেছে। তা বেন্ড করেছে কথাটার মানে কি? কথাটার মানে হলো যে ট্যানজেন্ট ভেক্টর অ্যাট এভরি পয়েন্ট তুমি যখন আঁকছো, ডিরেকশনটা কতখানি বেঁকে যাচ্ছে, কতখানি কার্ভড হচ্ছে, সেই যে কোয়ান্টিটিটা আমাকে বলে দিচ্ছে, দ্যাট ইজ কার্ভেচার। সেই জন্যই কার্ভেচারকে বলা হয় one of the fundamental property of the curve which gives the shape of a curve. Another one is torsion. It is also very important in the true sense of space. এবং এখানেও যেটা আমি সারফেস পড়াবো যখন, I will give you the concept of relativity. Interestingly, Gauss, when defined the curve, he narrated the definition as xi equal to xit, which I have given you earlier. Actually, this is the definition of a space curve. That is a curve lying on a space. Whether you are taking the dimension to be I equal to 2, I equal to 3, I equal to more than 3, that is up to you to decide, because it will depend on the metric of the space. Fine. But what is then plane curve? Plane curve is the concept which gives the torsion. Torsion, what? I have already told you that if you go to the intrinsic differentiation of the binormal vector, then it will give a scalar quantity which is termed as torsion. Torsion is such that it can be 0, it can be positive, it can be negative. Now the basic question is, immediately you will ask me, well, whenever you are defining curvature, you are saying, let us accept curvature is greater than 0. If it is 0, let us accept the curvature is greater than 0. Sorry. Otherwise, if it is 0, then it is a straight line. But in the case of torsion, you are saying it can be greater than 0, it can be less than 0. How? Okay. Here lies also the difference, and that concept is also a very powerful concept in the geometry that is known as orientability. What does it mean? I will give you the answer. Let me explain the torsion at first. So the scalar quantity is such the intrinsic differentiation of the binormal. And what is binormal? I have told you, binormal is such a vector, it is orthogonal to the tangent vector, it is orthogonal to the normal vector. Now you just think of a curve drawing on your exercise book. You can think that binormal is such that it is the vector which is orthogonal to the plane determined by tangent vector and normal vector. Or in a nutshell, I can say that your exercise book or your plain paper is also of dimension 2. Why? Length and breadth. These are the two independent vectors. In the true spirit of algebra, I can say that these two are the basis of R2. R2, dimension 2, the basis, number of elements in a basis will be 2. And the geometric point of view, my exercise book can be thought as a replica of two-dimensional space. So what is your binormal then? Binormal is a vector which is orthogonal to the plane. So if I draw just a curve, and if I think that this curve is lying on my plane only, then the torsion will be equal to 0. That means geometrical interpretation of the torsion is this. Torsion gives, or torsion measures the extent, whether the curve is a plane curve or whether the plane curve is not a plane curve. Now, again you think of a cylinder. Cylinder is a figure which can be thought in a space of dimension 3. You can think of a curve, that means a coil, electrical coil. You are roaming this electrical coil round your cylinder in a two-type manners, either in clockwise or in anti-clockwise. I think I am clear to you. That means you are rounding your electric wire to the cylinder either clockwise or anti-clockwise. So the direction, if you draw a direction, আমি বলছি বাংলায় বলছি, if I draw a tangent at any point on the curve which has been rounded on the cylinder clockwise, or আরেকটা সিলিন্ডার তুমি নিলে যেখানে তুমি কার্ভটাকে রাউন্ড করেছো অ্যান্টি ক্লকওয়াইজ, তুমি পয়েন্টটা মোটামুটি দুটো জায়গাতেই এক নিয়ে তুমি যদি ডিরেকশন অফ দ্য ট্যানজেন্ট ভেক্টর ড্র করো, তুমি ওয়াচ করবে বা দেখবে তোমার ডিরেকশনে অন্যরকম একটা ফ্লেভার আসছে। অর্থাৎ ক্লকওয়াইজ ডিরেকশন অ্যান্ড অ্যান্টি ক্লকওয়াইজ ডিরেকশন, এইখানে তোমার যেটা ট্যানজেন্ট, নর্মাল, বাইনর্মাল যে ওয়েতে আসবে, ওইখানে তোমার ট্যানজেন্ট, নর্মাল, বাইনর্মাল উল্টো ভাবে আসবে। হোয়াট ডাজ ইট মিন? আমরা সাধারণত ক্লকওয়াইজ, অ্যান্টি ক্লকওয়াইজ ডিরেকশনটা যখনই আমরা ক্লাসে বলি, আমরা কি বলি? এটা কনভেনশন থ্রু আউট দ্য ওয়ার্ল্ড ইন দ্য জিওমেট্রি, অ্যান্টি ক্লকওয়াইজ অর্থাৎ ট্যানজেন্ট তুমি ড্র করো, তারপরে তুমি নর্মাল আঁকো, তারপরে তুমি বাইনর্মালকে চিন্তা করো। বাইনর্মালের বাংলা, বাইনর্মাল আমি ঠিক বলতে পারবো না, আই এম ভেরি সরি। ট্যানজেন্টের বাংলাটা বোধহয় স্পর্শক, নর্মালটা বোধহয় অভিলম্ব, বাইনর্মালের বাংলাটা আমি জানি না। তার কারণ অ্যাকচুয়ালি এই যে কনসেপ্টটা, এটা পিজিতে পড়ানো হয়, এটা আমরা আন্ডার গ্র্যাজুয়েটে এনেছি। এখন আন্ডার গ্র্যাজুয়েটে বেশিরভাগ কনসেপ্টই আমরা বাংলায় লিখতে পারি, কিন্তু বাইনর্মালের বাংলা আমি এখনো জানি না। এক্সট্রিমলি সরি। বাইনর্মালকে তুমি চেয়ারকে যেমন চেয়ার বলো, টেবিলকে যেমন টেবিল বলো, এটাকেও তুমি মেনে নাও, বাইনর্মালকে বাইনর্মাল। আই এম সরি, তুমি এটা অ্যাকসেপ্ট করে নাও। কেমন যে এটাকে বাংলা এক্ষুনি করা যাচ্ছে না। ওকে, তুমি এইভাবেই কনসেপ্টটা রাখো যে আ ভেক্টর which is orthogonal to the tangent and normal. Thank you, Pritimoni. তার মানে this is the vector which is perpendicular to the plane determined by tangent and normal. তাহলে এই যে চলাটা সে অ্যান্টি ক্লকওয়াইজে যাচ্ছে না ক্লকওয়াইজে যাচ্ছে, খুব লুজলি স্পিকিং এটাকেই আমরা জিওমেট্রিতে বলি ওরিয়েন্টেশন। সো if the orientation of a curve is anti-clockwise, then I will give you the answer. Area cannot be negative. It's a basic question in the school, my dear. Area is a scalar quantity, okay. So if the torsion is greater than 0, we will say the curve has an anti-clockwise orientation. And if the torsion tensor is negative, then we say the curve has a negative or clockwise interaction. এই কনসেপ্টটা দিয়েই আমরা এবার যেটা আনি সেরেট-ফ্রেনেট formulae. This is also a powerful concept of a curve. এইটা আর কিছুই নয়, সেরেট-ফ্রেনেট formulae means these formulas were deduced by Serret and Frenet, and that's why nowadays is called as, oh yes, binormal is not binomial. He's quite interesting student. Binomial is a concept in the algebra, my dear. I binormal. Normal, you just put bi. That is why it is binormal. That means it is associated to your normal vector. Okay. Binomial is a word in the algebra. Okay, fine. So Serret-Frenet formulas are the three formulas which gives the intrinsic differentiation of the tangent vector, normal vector, and binormal. So to study a space curve, these three are the vital equations, and curvature and torsion will give you the nature of a curve. Now, another concept in a curve which I want to mention today is geodesy. Why? I wish to describe geodesy because geodesy is also a concept which you have already studied in the school, but we have not uttered this word in this manner. Geodesy means it is the curve which will give the minimum length between the two distinct points. Now, this definition seems to be quite irritating to many. So let me explain right from the school days. Whenever you are drawing a straight line in your exercise book, you just choose two distinct points on your straight line. If I ask you which is the minimum distance between these two distinct points, or in the undergraduate course, if I ask you which curve will give you the minimum length or minimum distance between these two distinct points, then you will at once give me the answer, okay, ma'am, it is straight line. It is not a curved line, but it is absolutely a straight line. So straight line is the geodesy in R2. Or I can say, if I draw R3 a figure, say for sphere, then again I have to think that which will give the minimum length. So for that, I need a theory. Because in the undergraduate course or in the school level, whatever we teach geometry, I have uttered this word in my first lecture, which I want to mention here again, that geometry can be taught in the three ways. One way is axiomatic approach, one way is analytic approach, and the third approach is empirical approach. Empirical approach is nothing but the vision, line, and etc., which is mainly done in school. Analytic approach is the approach of studying the geometry which is taught in college. And this approach is due to René Descartes, a French mathematician, who gave the concept after Euclid. This concept was given a little bit by your principal at the inaugural lecture. If I have time, I will explain after my today's lecture. But axiomatic approach is the powerful approach of studying geometry, but this approach needs a matured brain. And this is the approach which we teach in the postgraduate course, and that is also another story. So now let us come back to geodesy, which is also a very interesting topic in the undergraduate course. So to determine the geodesic equation, we need a device which has been given by the great mathematician Euler. It is known as Euler Method. You can study it from any textbook of tensor, but the concept I will explain. This equation, when it will come up in the last line, it is nothing but a second order differential equation. Now, if it is a second order differential equation, you will find that some terms, first terms, it says, say for example, d2y dt square plus Christoffel symbols with coordinates equal to 0. Again, see the beauty of tensor. And that is why Einstein took this device or took this method. Why? Because I have already told you that in the space R2 and R3, there is no question of Christoffel symbols, because Christoffel symbols is nothing but the partial derivative of the metric tensor. And the metric tensor of the Euclidean space has the value either 1 or 0. So the partial derivative is 0. So there is no question of Christoffel symbols in the Euclidean space. And that is why whenever we teach geometry in the undergraduate course, up to undergraduate course, we teach R2, R3 only in the vector notation, because we don't need the notation of tensor. But whenever we change the dimension of the space to be greater than 3, that means the metric has been changed as Gij, dxi, dxj. That means the coefficients are Gij. So you can have the partial derivatives of Gij, and that determines Christoffel symbols. So this is the equation of the geodesic equation. But again, I have told you that in the research, we accept any notation as a generalization of the original notation if we can show you that, well, this equation or this concept is true for n equal to 3. See, this equation is such that whenever we are putting n equal to 3, all the Christoffel symbols will vanish. So you will come up with d2y dx square equal to 0. You just take the integration. Ultimately, you will find the equation of straight line in the Cartesian system. So we call this second order differential equation as the geodesic in a space of dimension n. Now for n equal to 3, if we just go to the equation of sphere, it has also 2 parameters. I will come when I will come of surface. Then it can be shown, you just accept this statement that the geodesic on a sphere are nothing but the great circles. This can be deduced. It's not at all a complete or contradictory, or I can say that it's a very hard problem. No, not at all. It's very easy. If I just tell you that you do in this manner, you can at once calculate that this is the geodesic equation for the sphere, which is nothing but the great circle. Now to complete the curves in the undergraduate course, I can say that after this, these 2 concepts, space curve, plane curve, parallel vector, geodesy, after that, you will come up with some notation, developable, etc., etc. And these also can be taught in a lucid manner. But just because I have another topic, surface, and the time is also showing that I have left a very few minutes, let me switch over to surface, which is also another concept which is very interesting and very beautiful also. See, if I say surface, you can think, let me say at first, that think surface as a subset of R3. If I say subset of R3, then you will tell me if it is a subset, whether its dimension is 3 or it is less than 3. So to clarify, this definition, we will go to the help of Gauss again. He narrated or he defined the definition of surface beautifully again. See, he told us that curve is such that you can think of coordinates, you can think of points whose coordinates are function of a single parameter. It's a beautiful concept. He said that, well, you think of a geometric entity such that all the points have coordinates who are functions of two parameters. And in every book of tensor, these two parameters are written by either by U1 or U2 or by UV. That means two parameter. So if I say that you just think of a surface as a subset of R3, in the point of view of geometry, I will say you think as totally immersed in R3. That means in the true spirit of algebra. Totally immersed. Now what will happen? This concept will give you the concept of relativity. How? You just think of x-axis, y-axis, z-axis. And you think of the first quadrant. And you are drawing a just set notation on that first quadrant. So for any point, according to Gauss, we are saying that they are the functions of two parameters, u and v. Again, come back to the notation of school. School geometry, we have told you what is the distance between the two neighboring points. You know the distance between the two neighboring points in the high school, and we have given the notation. So in the surface also, you can choose two distinct points, and again, for two distinct points, you have the coordinates just like R2 in the high school. So in the same manner as taught in the high school, we will deduce the distance between the two distinct nearing points on the surface in the tensor approach. And the metric which you find in RT, here also you will find a metric. This metric is called the first fundamental form. So first fundamental form gives the distance between the two distinct neighboring points on a surface lying immersed or totally immersed on a higher dimension. But we are not considering the higher dimension. So if we consider the higher dimension, or in the physicist way, or in the spirit of Einstein, if I say that what will happen the metric if I consider in a neighboring space, that means the observer is in the neighboring space. That means the observer is in a space of dimension higher than that of the surface. See, for example, if I say that I am in the space n equal to 3, and I am watching what is happening on my exercise book. So the observer in a space of dimension higher than that of the surface we are considering. So what will happen? Because of the observer, that binormal which we have taught in the curve locally, it will come up as a whole, as a normal vector of the whole space. And that is denoted by xi, again by Greek letter, and it is termed as surface normal. And the inner product of the surface normal and the position vector of that particular point will again give you a metric. It is again a distance function, but distance function is with the surface normal and the position vector of the point. That is why its metric is termed as second fundamental form. This is the basic difference between the first fundamental form and the second fundamental form. First fundamental form, second fundamental form, both these give you a metric. But the basic difference is that 2 points are on the surface. You are also in the surface. That means no question of understanding or thinking outside. In the physicist term or in the term of Einstein, no question of relativity. I am not watching the happening or phenomena relative to my position. I'm just watching what is happening on my paper. And that gives the first fundamental form. But if I wish to watch what is happening, that means my pressure is also on that particular event relative to me. That also gives a metric, and that is second fundamental form. And this second fundamental form is such a powerful concept that if I say how many surface normal will be if I just utter the dimension of the space and the dimension of the surface where you are immersing that, we will at once tell you what will be the number of surface normal. I am coming up last stage. I'm just giving you a little bit of answer of this particular question. For example, whenever the Euclidean space n equal to 3 and your exercise book, it is n equal to 2, we can show you the surface normal, and we always tell you that you just take a pen or pencil on your exercise book perpendicular to your plane, and this gives you the normal vector. So the number of normal vector is 3 minus 2, that is equal to 1. Now when we are going outside this universe, if it is so, mathematically, the space is of dimension m notation, that means say matras m. And if you are considering a space which is totally immersed in that particular space and its dimension is n, and if the dimension n is less than m, then it will be immersed. How many surface normal? Surface normal will be m minus n. Now if you ask me, show me these normals, I will say, I am helpless. I cannot show you the number of normals. Then what is the beauty or what is the fun of studying geometry then? The fun is that if I consider n equal to 3, then I can show you the normal, then I can show you or draw you or picturize you. That is why geometry is also told as you can picturize the concept. If you can picturize the concept, then that is your geometry. If you can't, then that is abstract way. But we, the geometer, tell that no, it is not the abstract. It is the matured brain who can think of that is also a space. And in that immersed space, the number of normals will be m minus n. Now, how can we teach this concept? This is the third chapter of the tensor notation of studying differential geometry in the undergraduate course of the University of Calcutta. And the two equation which gives this concept, it is also a French mathematician. One is by Gauss, none other than Gauss, the famous mathematician all time. And another one is the Menardi-Kodaji equation, which will give you the number of surface normal. And it is the last chapter. And this also gives another kind of curvature. And blah, blah, there are lots of curvature, principal curvature, etc., which I don't want to mention again here because maybe some people will feel bored. So to brush up or to sum up today's lecture, I can say in one line that to study a curve, the basic fundamental object is curvature and torsion. And the basic fundamental concept to study surface is nothing but Menardi-Kodaji equation and Gauss equation, and also the immersion. And again, the differentiation which we do in that particular surface, that is also a completely different from the intrinsic differentiation and the covariant differentiation. And that differentiation is known as the tensor differentiation or tensor derivative. But that is a different topic. So I must stop here. If you have any question, you can ask me. And again, thank you very much. Not only the participants, but also my colleagues as a patient hearing. Thank you.
Thank you, madam. Thank you. I listened.
হয়তো তুই অনেক কিছু জানিস।
না 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 না, এই জায়গাটা সাবজেক্ট তো বেশ আমার কাছে নতুন, মানে জিওমেট্রিটা।
আসলে এটা সোজা করে বললে খুব মজা লাগবে। আচ্ছা, কি লিখেছি? Does multiple dimensional space have parallel dimensions? You can't tell parallel dimension. That is no word of parallel dimension, but well, the convener, Shantanu and Aditi, will you give me just 1 minute to answer this particular question? Hello, Aditi.
Yeah, madam, you can answer. I think Aditi has some problem.
There is a question on parallel line. আচ্ছা, এটা আমি একটু জাস্ট বলি। আমার মনে হয় এই কোয়েশ্চেনটা তারাই করেছে যারা পিজি করছে, তা না হলে এই কোয়েশ্চেনটা তারা করতে, মানে আন্ডারগ্রাজুয়েটের কোনো স্টুডেন্ট এই কোয়েশ্চেন করবে না। প্যারালালের কনসেপ্ট ম্যাচিউরড ব্রেন। সি, জাস্ট একটা লাইনে বলছি, তোমাদের প্রিন্সিপাল ইন্ট্রোডাকশনে এই কনসেপ্টটা টাচ করে গিয়েছিলেন। ইউক্লিড যে জিওমেট্রিটা আমরা পড়ি সেটা দেখবে আমরা স্কুলে কোনোদিনও বলি না ইউক্লিডিয়ান জিওমেট্রি। উনিও প্রিন্সিপাল এই কথাটা বলেছেন। ব্যাস, আমরা বলি না কেন? বিকজ উই ডোন্ট নিড ইট। জিওমেট্রি ইজ জিওমেট্রি। বাট when you are in the upper class, high school, there is a little bit of question, parallelism. What does it mean? Euclid gave the concept of parallelism in a different manner. And this concept was such a controversial. For 2000 years, throughout the world, people wanted to prove it, but they failed. And their failure constitute the concept of non-Euclidean geometry. Just imagine, Euclidean geometry, non-Euclidean geometry. ব্যাপারটা কি? ব্যাপারটা হচ্ছে, you have already heard or mentioned Professor M. Shah one word, axiom, and he have mentioned that axiom is such, axiomatic method. It is the concept given by Hilbert, the famous Hilbert of functional analysis, that to study a concept, we have to start with some statements for which no proof will be given. And that is known as axiom. Euclid also gave one type of statement which is known as fifth axiom, and this is the parallel axiom, which tried by the mathematician throughout the world for 2000 years. এটা প্যারালাল সাবস্টিটিউটটা কি? তোমাদের প্রত্যেকের জিওমেট্রির বইতে এটা আছে স্কুল লেভেলে, কিন্তু এটা কিন্তু ইউক্লিডের অ্যাক্সিওম নয়, কিন্তু এটা হচ্ছে সাবস্টিটিউট ফর ইউক্লিড অ্যাক্সিওম, Playfair's axiom. Playfair's axiom means what? Given a point, given a line, such that the given point is not on the given line, then there exists one and only one line on the given point parallel to the given line. This is known as parallel axiom of Euclidean geometry. বাংলাটা মানে কি? আমি তোমাকে একটা লাইন দিলাম, মনে করো স্ট্রেট লাইন। লাইন বলতে ইউক্লিড স্ট্রেট লাইনই বোঝাতেন। একটা পয়েন্ট দেওয়া হলো, যে পয়েন্টটা ওই লাইনের উপরে নেই, সরি, ইউক্লিড কি বললেন? ওই পয়েন্ট দিয়ে তুমি একটা মাত্র লাইন টানতে পারবে যে লাইনটা প্যারালাল টু দ্য গিভেন ওয়ান। এটাকেই বলা হয় প্যারালাল অ্যাক্সিয়মস অফ দ্য ইউক্লিডিয়ান জিওমেট্রি। তাহলে দেন হোয়াট ইজ নন ইউক্লিডিয়ান জিওমেট্রি? আসলে নন ইউক্লিডিয়ান জিওমেট্রিটা হচ্ছে থ্রু আউট দ্য ওয়ার্ল্ড all the mathematician, আমি তোমাদেরকে বললাম, tried to prove it, this axiom, they failed. ফেল করতে গিয়ে তারা যে জিওমেট্রিটা তৈরি করে ফেললেন, it is also as consistent as the previous one, and one of them is Gauss also, কিন্তু Gauss never published his thesis. সেটাও একটা মজার গল্প, সেটা অন্যদিন বলবো। তাহলে এই একটা যদি প্যারালাল লাইন, এটা নেগেশন কি হতে পারে? আইদার কোনো প্যারালাল নেই অথবা মোর দ্যান ওয়ান প্যারালাল লাইন। তাহলে মোর দ্যান ওয়ান প্যারালাল লাইন যেটা, দ্যাট ইজ হাইপারবোলিক জিওমেট্রি, and that geometry has been invented by two, John Boloi from Hungary and Lobachevsky from Russia. আর যে জিওমেট্রিতে there is no parallel line, that is Riemannian geometry, that is developed by Riemann of Germany. কাজে parallel axiom হয়, parallel dimension হয় না। ঠিক আছে, যে এই প্রশ্নটা আমায় করেছিলেন। থ্যাংক ইউ।
Ma'am, there is also one question by Bipin Kohli. Ma'am, dimension of circle is 3, but when we write its question, write its equation, there are only 2 independent variables. Please explain.
How
Please
can you
start
say
with
the
what?
dimension of circle is 3?
Circle is 3. Yes, yes. Bipin Kohli.
Is Bipin Kohli present in the still now? Hello.
Ma'am, Bipin Kohli is in YouTube.
No,
Bipin
that
Kohli
is
is
why
in
I'm
YouTube.
asking.
So he is not here.
Okay. Maybe he is in the Zoom or something like that. See, dimension of a space. How can you understand or how can you think that what is the dimension? You just check the coordinates of the point. It is the click given by René Descartes. Whenever you are considering the dimension of plane R2, that is your exercise book, the coordinates of that particular point has component 2, x and y, abscissa and ordinate. So if you say the dimension of a space is 3, that means your spherical geometry, that is the 3-dimensional geometry, that means the point has 3 components, x, y, z. So when you are writing it, a circle, it is x square plus y square or something, if it is the center is 0, 0. So what is the coordinate? Coordinate is x and y. So how can you tell me that the dimension is 3, my dear? Maybe you are thinking of sphere. Sphere is in the space of dimension 3. That is why x square plus y square plus z square equal to 1. If you are considering a sphere of radius 1, center is 0, 0, 0. Am I clear?
I think doubts are clear.
Okay.
Anyone have any
Aditi,
question?
yeah, I am
Yeah.
seeing that Dinesh Mishra, he has a question.
Yeah,
If we
Dinesh
consider
Mishra.
two,
Yes.
if we consider 2
consider
points in a, yeah, you carry on.
No. Ma'am,
The
if we
question is,
consider 2,
if we consider 2 points in a paraboloid opposite to each other, then how can we measure the distance? That is the question.
Okay. You are mentioning paraboloid. Paraboloid is a concept in a 3-dimension. Okay. So if you are considering a point in a 3-dimension, so you have to measure the distance between these two with the help of geodesy. The geodesy equation will give you the length of the vector. The point, that means you have to draw the curve. Paraboloid, you have mentioned paraboloid. That means you are considering in a space of dimension n equal to 3, my dear. If you are not considering the point in a parabola, if you are considering a point in a parabola, choose a point and choose another point, then the distance will give you from the mathematical expression of the parabola with the help of something mathematical calculation is there. Right now, you cannot tell that this is the answer. You have to calculate it. But if you are considering paraboloid, then it is not so easy. No, tangent and binormal cannot create metric. Metric means what? Metric means a quadratic form. Okay? Quadratic form of what? The distance between the 2 distinct points in a space. যেটা শুভেন্দু যে প্রশ্নটা করলে বা করেছো, মেট্রিক কথাটার মানে আমি জানি না, তোমার আন্ডার গ্রাজুয়েট তুমি যদি এখনো পড়ো, তোমরা মেট্রিক স্পেস পড়বে। মেট্রিক স্পেস মিনস একটা কোয়াড্রেটিক ফর্ম, অ্যালজেব্রা দিয়ে বললে আরো সোজা হয়, একটা কোয়াড্রেটিক ফর্ম। জিওমেট্রিক্যালি আমি কিভাবে বলছি যে তুমি কি করে পাবে, অত দূর চিন্তা করতে হবে না শুভেন্দু। তুমি ক্লাস 11-12 চিন্তা করো। ক্লাস 11-12 এ n = 3 বলে আমরা পড়াই একটা পয়েন্টের কোঅর্ডিনেট x1 x2 x3 and the neighboring পয়েন্টের কোঅর্ডিনেট x1 plus dx1 x2 plus dx2 x2 plus dx3। ঠিক আছে? তাহলে এবার যখন আমি ডিসটেন্স বার করছি, তার মানে ইউ হ্যাভ টু টেক দ্য ডিফারেন্স বিটুইন দিস টু। দ্য ডিফারেন্স বিটুইন দিস টু হচ্ছে dx1 dx2 dx3 হোল স্কয়ার করছো, dx1 হোল স্কয়ার প্লাস dx2 হোল স্কয়ার প্লাস dx3 হোল স্কয়ার। So it is nothing but the metric quadratic form. So the tangent binormal is the concept of a curve. Or metric means the distance between the two distinct points. Am I clear, Shubhendu? Okay.
If Shubhendu is listening, please. No, I am asking why.
I'm asking why is into fine. Okay. If you cannot introduce metric, you cannot study the space, my dear. To study a space, you have to know the metric.
For studying space, metric has been introduced, but what's the specialization or beauty behind it? It may have the different beauty, that's why it has been introduced. That's my question. I want to know what's the beauty behind it. What's the word it does for us?
Yes, of course, beauty is there. See, whenever there is the metric, you at once watch the expression. The metric of the Euclidean space, you have the coefficient either 1 or 0. Then you at once tell that this is the Euclidean space. This is the trivial space where we stay. But it may happen that there are different types of space. So for the different space, you will have different metric. For example, Riemannian space, which has been introduced by Riemann, which is the generalization of the Euclidean space, যে স্পেসে আমরা আছি। এবার আরেকটা স্পেস বলি, যেটা আইনস্টাইনের স্পেস, স্পেশাল থিওরি অফ রিলেটিভিটি, সেটা হচ্ছে শুয়ার্টজের মেট্রিক। সেখানকার মেট্রিকটা দেখো, ওই যে এখানে যেমন জিআই যে রয়েছে, ফাংশনালটা হয়ে যাচ্ছে তোমার কোএফিশিয়েন্ট মেট্রিক ডিপেন্ডিং অন দ্য কোঅর্ডিনেটস জিআইজে। এটা অনেক ম্যানেজেবল। জিআইজের ভ্যালু আইদার 1 or 0 হলেই অটোমেটিক্যালি তুমি বলে দেবে ওকে, তার মানে আমরা যে স্পেসে আছি। কিন্তু আইনস্টাইনের যে স্পেশাল থিওরি অফ রিলেটিভিটির মেট্রিক, সেই মেট্রিকের চেহারাটা হচ্ছে 4 dimensional 1 1 1 -1. So metric is the beauty of studying any space. এবং Schwarz's metric ওটাই ছিল ক্লু আইনস্টাইন যেখানে রিলেটিভিটিতে গেলেন। Metric is a very powerful concept for studying a space. Am I clear?
Yes, ma'am. Thank you, ma'am.
Okay. I think we can.
Ma'am, there is one question. Kullan Jyoti Sardar from ma'am, curve আর ফাংশনের মধ্যে ডিফারেন্সটা একটু বলুন।
বাবা, ফাংশন তুমি আচ্ছা, may I ask you one question? What is your
ma'am, Kullan Jyoti Sardar is in YouTube session.
Oh, acha. Actually, okay. If your background is in the undergraduate course, then you see the function is just when we define a function in the 11-12 also, it is a relation between, I can say in a very naive manner, that from one set X and another is Y. So that is the relation between one set to one set. How can I give a relation between some 2 points from one set, which I said domain and range? Function is just a relation. That's why we sometimes say it's a mapping between X to Y, and so many X, Y is a basic. That is the same. That means it's a relation, or I can say I can cooperate between 2 sets. Just a relation, or just a coincidence, or just a mapping. So this is function. And he's asking that what is the relation between function and metric? Am I right, Aditi?
Yes, ma'am. Yes.
Metric, I think now it is clear. Metrics, there is no question of function of metric. Metric means it is a term. What does it mean? It means that with this mathematical expression, you can nature, or you can study, or you can think what is your space. The space where we do belong, where we are staying, the geometry of this space is Euclidean. And that is why we say that we stay in a space of Euclidean geometry. And if I say, what is then the mathematical expression? Then the mathematical expression is termed as metric. Now, if you ask that if Einstein stays in a special theory of relativity space, then what will be the mathematical expression of that space? Then I will write it as dx square equal to dx1 whole square plus dx2 whole square plus dx3 whole square minus dx4 whole square. So this is the expression mathematically of the space where we do live. Einstein's general theory of relativity, it is the space of fourth dimension. So function and metric is completely, totally different notation, totally different understanding. Okay, thank you very much.
Okay, I think almost all doubts are resolved. On behalf of entire family of Fakir College, thank you very, very much, ma'am, for this splendid and enriching lecture. By this beautiful lecture, we conclude the technical session. We are very much thankful to both of you, sir and madam. We arrive at our valedictory session. I am inviting Srimati Tiyash Chakraborty for the vote of thanks speech. Please, Tiyash. Tiyash, am I audible?
Am I audible?
Yes, you are audible and visible both.
Okay. Good evening, everyone. I deem it a great honor and privilege to propose the vote of thanks on this memorable event. First and foremost, I, on behalf of Fakir College Mathematics Department, would like to give a very hearty vote of thanks to our honorable speaker, Professor Montu Shaha and Professor Monjusha Mojumdar, for gracing today's webinar. They have managed and gave us some of their valuable time from their busy schedule and make this webinar a very meaningful and interesting one. I would like to thank the distinguished audience that involves eminent professors, research scholars, and wonderful students who have turned up in such a huge numbers and make our effort successful. I would like to express our deep gratitude to our principal sir, Dr. Shomen Chando, for his intense support and unbounded contribution behind this webinar. Now, I would like to thank our IQAC coordinator, sir, Dr. Programoy Pal, for his glorious presence and valuable suggestion for conducting this webinar. We are also very grateful to Dr. Liton Balo for his intense support in the technical field, as a result of which this webinar is conducted so smoothly, even on this virtual platform. I am happy to express a vote of thanks to our convener, Dr. Aditi Vishwas, who has made this webinar a grand success through her hard work and dedication. Last but not the least, I thank all the faculty members of Mathematics Department, Fakir College, for their cooperation and suggestion to make this webinar a resounding success. Once again, I thank you all for your glorious presence that turns this webinar into a grand success. Thank you.
Wishing you all the best. We conclude our state level webinar with this valedictory speech. Thanking you all for attending this lecture, cooperating us, and for your guidance. Thank you very much. End kori.